All right. Hi, everybody. This is Brandon Litherland from NASA Langley. Just doing a quick audio check, seeing if everyone can hear me and see the presentation. The stream looks pretty good from here. I know there's a little bit of a delay from when I speak to when it gets out to you, but hopefully it's not too long. See, we've got people already jumping in the chat, which is good. Nice to see everybody. All right. Thank you, Karen. I appreciate that. All right. Well, we are going to go ahead and start with the introduction to the 9th annual OpenVSP Workshop here in 2021. Again, fully virtual and streaming to our OpenVSP Videos channel, which you're all watching right now. The next 3 days are going to cover a variety of topics, updates, ongoing work, technical demonstrations, etc. So with that, we'll go ahead and get started. So again, we're fully virtual this year to try and maintain social distancing practices, eliminate the need to travel. The pandemic is still going strong, unfortunately, but for all of you out there, that means that there's no fees, there's no registration. You can join this stream anywhere that you want, and it's free and open distribution. So feel free to share the links to the workshop page or the sessions through social media, within your own working groups, to your friends or family. Anybody that you think might find this stuff interesting, feel free to share it. It's fully open. And we'll start with a few reminders here to our viewers that for the technical demonstrations, particularly those with small text, you'll want to upgrade your quality to 1080p. So sometimes YouTube doesn't do this automatically. So you'll want to check your quality just to make sure that you can see everything well. And if you are going to try and follow along with some of the tutorials, we recommend you watch, say, on your phone or a separate device if you can, because that gives you a full workspace to play with. Now, sessions will be recorded and uploaded for viewing later in case something happens where you can't join in or you want to look back on these. So it'll all be set up just the same as we did for the 2020 workshop. For our presenters that are joining or have already joined, either close or mute the VSP Live YouTube stream so that we don't have glitchy audio feedback, and maximize your presentation so that we get the best resolution out of the monitor. If you have videos or sound that you're trying to share, when you share your content, please include computer sound. And share the display that's closer to a 16:9 aspect ratio, or try and use as much of the screen as you can. So only the moderators, namely myself or Rob, or perhaps one of the others, should be on the Teams meeting at any time to try and avoid any issues with bandwidth. And so with that, let's go ahead and jump into a discussion about how the workshop is going to go over the next few days. So today is the first session. We're going to run from noon to about 3:15, maybe 3:30 Eastern today. And then we could perhaps have a little bit of time for, say, a Q&A session at the end if there's interest in that. Tomorrow, we're starting about a half an hour late at 12:30 Eastern and running all the way to 4 p.m. And then on the third day, we have everything scheduled from noon to about 2:30 or 3, and we have some time there at the end of the workshop to have some open discussion with everybody. On the OpenVSP Workshop 21 main page, you'll find all of the links to these YouTube live streams, and those can also be found here in the OpenVSP videos description. If you click Show More, it will drop down and bring you here. And then we have the VSP Conferences I.O. session provided by Ames Research Center, where you can post questions and you can vote on the ones that you want answered the most, and then either myself or Rob will try and do our best to answer those either in a written format or have the presenters answer them for you. So today, we're starting off with a workshop and an introduction and overview, and then we'll start getting right into VSP Aero updates with Dave Kenny, followed by some modeling best practices for that tool and some demonstrations. And we'll close out the day with M4 Engineering, talking about their M4 Structure Studio and some updates there. Tomorrow, we'll talk a little bit about CompGeom and meshing in OpenVSP, and go into some updates, feature additions, and improvements and demonstrations with Justin Gravitt from ES Aero. And then Flight Stream will follow along with two discussions, namely their acoustic toolbox and some viscous coupled flow solutions. And then we'll give a technical talk about the wave drag analysis. And then Nat Breton, who was a student here at NASA Langley, will give a presentation on a custom split flow turbofan model that they were able to build as a custom component for VSP. The third day, we're going to give a quick update on the OpenVSP ground school and let you know what's complete and what's coming around the bend. Do some technical presentation throughout the day. Grady Pastor from Auburn will be talking about propeller optimization. And we'll close out that day with a tour of the OpenVSP source code. So this is not the same thing as we did last year where we talk about how to build it from the source, nor is it a discussion of the API. This is the source code itself if you want to get into development activity. So if you're interested in that type of thing, I really recommend that you join in at 2:30 on Thursday. And with that, I'm going to go ahead and start walking through the slides, and Rob McDonald is going to take over for an OpenVSP overview and talk about really what it's for, what it does, and where it fits in the design process. So let me mute my...
Thanks, Brandon. Can you share your slides through Teams so I can see them live? That looks great. Thank you much. So, good morning, good evening, good night, wherever you happen to be. I'm Rob McDonald. Most of you may, if you've been to one of these workshops before, you've probably seen these slides, but they're always a nice warm up to get us started and into the mood for a workshop, and get people thinking about what OpenVSP is and what it's for. I like to think about geometry as the start of almost everything we do as engineers. When you took a statics class, you probably learned to start with your free body diagram. And so we're used to starting our engineering analysis activities with a drawing. And so really so much of engineering is fundamental to the shape of whatever we are analyzing or designing. And that's really the truth, whether we're doing aerodynamics or manufacturing or acoustics, air elasticity, all these different disciplines. So shape is a common denominator for engineering analysis. However, in practice, there's seldom any actual commonality. In practice, these tools, these analyses have very different needs from the geometry. And of course, since their codes and their methods and their techniques, their theory, all developed separately, their geometry needs develop separately. And so in a workflow, when you're designing an aircraft, you'll often find that you end up needing multiple geometry models of a single aircraft. It's very inefficient, very redundant, and kind of a pain in the butt. Next slide. So the fact is that none of these things are actually, when we do the analysis, none of these representations correspond to the true geometry, meaning the real true shape. If you were to go out and put your hands on it, what usually happens is you'll have someone build a CAD model with a single intent. You'll make a model for aerodynamics. You'll make a model for manufacturing or for, integration of maintenance or structures. And each of these different CAD models have different simplifications and different limitations. Different decisions have been made in constructing them in order to feed their analysis tools, in order to capture the intent. An aerodynamics model only needs the outer mold line. It doesn't need the interior bulkheads and the seats and the engines and everything on the inside of an airplane. But even on the outside of an airplane, you'll typically remove all the fasteners and a lot of seams and gaps and things that show up in manufacturing because our meshing techniques and our computational analysis simply doesn't have the level of detail to capture all of those things that might instead be included in a CAD model meant for manufacturing where you're going to go directly to CNC and cut parts. So we need to recognize that, there isn't necessarily one true model. And the geometry model of an airplane varies where we are in the life cycle of the aircraft, from conceptual design all the way to production and even post-production and support. Next slide. There's also a gap in how we do geometry. The historical way was that every analysis tool had its own geometry model, and that geometry model was built into that tool. And that model satisfied the needs for that tool and that tool alone. And I've seen cases, for example, of an old aerodynamics code whose source was about 500 pages of Fortran. About 100 pages of that was the solver. A large chunk was memory management. Overwhelming majority was actually the geometry. And we don't even think about that as being a part of an aerodynamics tool, but you had to get your geometry somehow. So that's sort of the one way of doing it. A lot of tools still do that. The opposite approach really was born out of the finite element world, which is where you start with your CAD model and you use a general purpose CAD model that then you go through to a dedicated grid generation tool and through some pre-processing tools to lead into a finite element analysis. And that CAD-based approach is very general, but very labor intensive and requires a lot of other tools. But there's a fundamental gap between the geometry model and the analysis. And one of the main goals of OpenVSP is to try and fill this gap where, we're not, to get people away from using the analysis integrated, where there's a separate geometry model for every analysis, but also not being anywhere near as heavyweight as CAD and a lot of those difficulties. So that's where we're trying to fit in. Next slide. So there's also lots of problems with the fidelity opportunities and what exists in a design process. While there's many different levels of fidelity out there available to engineers in theory, what we find in practice is that you're usually not able to choose your level of fidelity freely. You don't get to choose it based on just simply the decision that you're making at the time and what it requires, but you often end up choosing the tool based on the other tools around you. For example, if the only geometry model you have of an aircraft is a high tool, then it's going to be very difficult to develop an equivalent stick and equivalent beam model of the structures. Or likewise, if your company is invested tremendously in a particular path from geometry to mesh to solver, and you've developed tools around that, and obviously you've invested a lot in licenses around that, you've tremendous expense in dollars and engineer time, that means that it's very difficult for you to perhaps go and use another tool that hasn't been invested in, perhaps a lower fidelity tool, a vortex lattice or lifting line theory, something like that, that might be appropriate for the decision you're making, but that really isn't an option because you haven't invested in that tool. So what we actually end up with in practice is, instead of a densely populated matrix from low fidelity to high fidelity across all the disciplines of an aircraft, we actually have a sparsely populated matrix where in any given discipline, we may only have invested in one tool path. And given that sparsely populated matrix, we don't have the ability to choose freely. We can only pretty much choose for each discipline, we can only choose one tool at a time. Next slide. So when I'm talking about geometry, we have to ask ourselves, what is the real shape? And in OpenVSP and in other tools, we have many possible representations of a single geometry. In the upper right, we have a representation that's perhaps a smooth mathematical surface. We have a wireframe, we have a stack of airfoils. You might have a thin surface, what we might call a potato chip, like a vortex lattice surface. You might have a rough triangulated surface in the center, or a nice, pretty mesh-generated unstructured mesh on the left. You could have a finite element mesh with ribs and spars and finite element nodes. You could have an equivalent plate model or even an equivalent line model. And all these different representations are the kinds of things that we feed to analyses, and they all represent a single geometry. And so one of the core ideas of VSP is to be able to feed all of these kinds of analyses, generate all these different representations from the single concept of the model, the single geometry representation. And in VSP, we like that geometry to be represented by parameters, the engineering parameters that are intuitive, things like aspect ratio, area, sweep, taper ratio, thickness to chord in this wing example. And that way, those parameters become the true geometry, and everything else is just a representation of that idea. Next slide. So a lot of people will make the mistake and think that that fidelity increases throughout the design process. And I'd like to make the argument instead that it doesn't. And I think we'll do that more on the slide after this. But right here, the representation definitely has to do with the fidelity of tool, where you'll use one representation like the thin surface on the left for vortex lattice code, maybe something in the middle, like in the middle for a panel code, or all the way over to the right for a CFD tool, where we have different meshes, different tools that relate to the order or the fidelity of that tool. Next slide. But that does not necessarily mean that's the process as it corresponds to the phase of design. It is not necessarily true that you always go from lower fidelity to higher fidelity as you go from conceptual to preliminary and detailed design. And examples of this, if you're designing a transonic aircraft, you may need to consider some interference drag concepts that can only be captured with a high fidelity aero tool. And you may need to consider some of those things in the conceptual design process. And at the same time, during detailed design, you may do some hand calculations when designing and calculating the loads on a rudder pulley bracket. And so there's times when you need high fidelity in conceptual design, and there's times when you need low fidelity in detailed design. And so we do not make the mistake of correlating that fidelity and these tools are a direct correlation to the phase of the design process. Next slide. Instead, what you should think about is what design phase you're in, whether it's conceptual, preliminary, or detailed design. It's not about how the decisions are made, right? It's not about the fidelity used to make the decision and to inform it. Instead, it's about what decisions are made. During conceptual design, you're making these bulk, big bone decisions, primary wing layout, what are the mission requirements, how are you going to achieve this? In preliminary design, you're nuancing things a bit more. You're deciding exactly the structural layout. You're nuancing the twist of the wing and maybe the camber of the wing. All the way to detailed design, you're lining up rivet holes. You're doing composite ply layouts. You're designing tooling, manufacturability. So you're making fundamentally different decisions in these processes. That's what changes through the design phase, not fidelity. Fidelity is an independent axis to this process. And obviously in VSP, we're focused on conceptual and somewhat into preliminary design, but we're also focused on letting you have all of the different fidelity tools that you need to make the decisions that you're making. Next slide. So OpenVSP is a parametric tool, and we come from a place where those parameters are the geometry truth, right? They are the ground truth. That's really where we start. And so the concept, that idea, this is a wing, this is a NACA 4-digit airfoil, the aspect ratio is 8, right? Those ideas, that is the geometry. And everything else is a representation. And, parameters work throughout this process. In the conceptual design process, we have these bulk parameters, things like aspect ratio, area, and taper ratio of a wing. In preliminary design, we add some more detail. We have twist as a function of span and thickness to chord as a function of span. Our wing planform gets more complex. We're nuancing high lift. There's a lot more parameters, but they're still parametric. When we go to detailed design, every part needs every detail laid out. And the idea, the same process of using parameterizations starts to fall apart because we can't really limit ourselves to the families of shapes. We instead need more general shapes that CAD lets us do. And so while there's still parameters there, it's a little bit less intuitive for parametric. So that's part of why OpenVSP is really best suited to conceptual and into preliminary design. Next slide. So hopefully this if this is your first workshop, welcome. If you've been to some before, we're great to have you back. We are doing things a little bit differently this year. In this year's virtual workshop, we're going to try and avoid a lot of repetition from what was available in last year's workshop. And that's because last year's presentations are still available on video. And so this year we're going to try and purposely avoid a lot of repetition. And so we'll be doing new things and updates, although some of it will be repeated from past workshops. And normally at this point, I do a show of hands in the audience to see who's been at every workshop or how many you've been to. But we'll just do a virtual show of hands. You guys can think about how many of these you've been to or if you've missed. And the other thing I'd like everyone to look at here is the current version of OpenVSP is 3.25. Think about where you are, right? Are you still using version 3.15? Are you using something else pretty old? And it's time to update if you haven't. There's no good reason not to. In general, there's a lot of progress that's made and a lot of changes made every version. So if you are using an ancient version, it's time to bring yourself up to the current day and to try and stay there where we can best fix problems and help support everyone. Next slide. So here's a short list of some of the things that have been added since the last workshop. One of the big changes was support for faster updates, and this one has been a bit painful. It's caused a lot of bugs, but I hope we've got most of them resolved, and I hope that everyone is seeing a much faster, more interactive process with OpenVSP and complicated models. Negative volume support's been added to MeshGeom, and a lot of the other computational solid geometry, the constructive solid geometry CSG tools that we have. We're developing a hybrid thick-thin surface representation. I'll show some of that later in the workshop. Some user interface things, resizable columns so that a lot of table outputs in the GUI are a lot easier to use and better show information. Enhanced airfoil types, enhancements to actuator disk, enhancements to FEA, really things across the board. A lot of improvements to the API documentation and the documentation tests. Big updates to the VSP Arrow solver, the viewer and slicer that go together. Dave Kinney will be talking about that in a moment. And support to that matching in the GUI. And just across the board, a lot of inputs, a lot of fixes and bug fixes. So lots of good reasons to stay up to date. Next slide. And I think that's all that we've got for this introduction. We've got some room here for questions in either the conference IO or over on YouTube. And we're not going to, if we finish this presentation early, we're not going to just dive straight into the next one. We're going to try and stay on the schedule throughout this 3-day workshop. That way, if anybody is timing their arrival so that they can capture a particular presentation, we won't lose that person. So we've got a couple of minutes here for any questions that Brandon or I are happy to take.
All right. Thanks very much, Rob. I appreciate the overview. So right now, I am presenting on, I've got my microphone going and desktop audio. So if anybody's catching any feedback on the live stream, let me know, and I'll get that sorted about as quick as I can. I'm going to go ahead and end this slideshow. So, yep, should bring that back up. Great. I'm going to stop presenting that and pop this on for just a second. So hopefully everybody can still see what's going on. Let's see. We've got some questions here popping up in the conferences IO. One of which is, can OpenVSP model flow and downdraft interactions for eVTOL aircraft? That's probably one that we'll pose to Dave here in a little while. And
I'll take a quick stab, and Dave can certainly address it more. I'd say you could give it a try. I know that it has been used, VSP Aero has been used to model aircraft and a propeller inside a wind tunnel. And it's also been used to model a propeller on a ground test stand where there was a building and a cinder block wall nearby. And so they were able to build models of those walls and then put the propeller in and look at how the performance on the propeller changed with those walls in proximity. So I know that that's been done. I think it depends a lot on exactly what you want to get out of an analysis like that. And I suspect you might want to do prescribed motion where you model the aircraft flying, say, through an urban canyon or approaching a building. And there's some support for unsteady analysis with prescribed motion, but that level of complex motion would be very difficult to achieve right now. So maybe Dave will have some answers for that down the road and ways to do that in the future. Um, and then there's also a question here. If anybody on YouTube is not on the IO site, you should join us there. But a question about control surface and high lift modeling capabilities and anything with a gap, right? Anything leading edge slots or slotted flaps Fowler is difficult to do in VSP. Um, and I think that basically the answer I have there is I have some ideas for how to do that. But large, challenging tool development like that needs to be, frankly, historically in VSP has been financially supported by a sponsor who's interested in that particular kind of work. And so, historically, that's usually the Air Force or NASA. Um, and we're working on whatever priorities there have been there. When I was working at Uber, I was obviously able to work on things that Uber prioritized. But so I would say that it's certainly possible. I have some ideas on how to approach that, but it's probably not going to happen. It'd be a lot of work, so it's probably not going to happen without the support of a sponsor who's interested in that particular work. And apologies if you hear a grumpy dog in the background. I'm going to go see if I can placate him.
Fair enough. All right. Yeah, there was an echo coming through on my microphone. That's because my microphone's picking up my speakers playing into the. Anyway, yeah, so we appreciate people pointing that out, and we've got it sorted. So we are going to take just a couple of minutes here and make sure that Dave Kinney is queued up and ready to go. And then here in 2 or 3 minutes, we'll begin at 12:30 with his presentation on VSP Aero updates. So we'll see you all here in just a little bit. All right, so it's 12:30, and we're going to go ahead and start with Dave Kinney's presentation on VSPAero updates. So I'm going to mute my microphone here, and Dave, we're ready for you.
Okay, hopefully everybody can see and hear me. This year, a little bit different than what I've done in the previous year. So in the past, I've spent quite a bit of time going into the details and the nitty-gritty theory of the solver and the vortex lattice versus panel methods. I am not going to talk about really any of that today. And as Brandon mentioned, all this is going to be recorded. But one thing he didn't mention, I don't think, is all last year's and the virtual presentations were recorded as well. So if you are interested in kind of the theory behind VSP Aero, I recommend you go and take a look at last year's workshop presentations, not just mine, but specifically for VSP Aero, where I basically gave the same spiel I've given previous years that go into the details of the solver. So today I'm going to basically spend time just going over what's new. It's going to be a little bit a higher level presentation, and definitely open to questions. I'll leave it to Brandon if he wants to bring them up while I'm going, or if we just hold them to the end. But there we go. So outline. Going to go over some new stuff. Just kind of like not really big stuff, but new stuff that there. Rob mentioned a little bit of it. Then I'm going to talk a little bit about some of the updates that have gone into the current version of the code, and that will going to be rolled out, whenever the next update gets pushed out. Specifically, just talk about stall prediction, some structural analysis support, some optimization support, and then a little bit about things that go round and round. So, just new stuff. The first one, Rob mentioned this, Reynolds number sweeps are supported. So, in previous versions of the code, you could run angle of attack sweeps, Mach sweeps, a combination of the two, and you basically get a square database across all the Mach and angle of attack cases. And you can now put in a list of Reynolds numbers, and it will basically write out a .polar file that has the solutions for CL, CD, CM, etc. as a function of Mach, angle of attack, and Reynolds number for all the Mach alphas and Reynolds that you put into the code. And the Reynolds number sweeps are really, essentially post-processing. The solver is an inviscid solver. It's either running vortex lattice or panel methods. And so the Reynolds number sweeps are basically a post-processing to make an estimate for the viscous drag. And as well, as we'll talk later, apply the stall model if you have that turned on. And so for the most part, doing those Reynolds number sweeps are almost free. They cost very little time in terms of solution time added into a Mach alpha sweep. Span-wise loading for panel mode. So in the past, if you ran the vortex lattice code, you got a load file that gave you basically span-wise loading information because that was easy to post-process out of the vortex lattice code. We support that now in the panel code. It's going to work best for the VSP geom file format that Rob is going to talk about later, but it does work for the comp geom meshes as well. But there are some caveats where it could get confused. For some moment calculations, there's actually a lot of work that's been done over the last year to improve the accuracy of force and moment calculations in general. That ended up in the current release that's out there being a bit slower than previous releases. It's just doing more work to try to do a better answer. The next release is basically back up to par, so I bought back some of that slowdown. So we'd pretty much be back at par where we were, and in general get improved accuracy for the force and moments. VSP geom support, so Rob will talk about that, but that's basically kind of merging both the panel and the vortex lattice models into a file format that in general could support both. And a little bit more flexible than what we had in the past. And then, as Rob mentioned, a lot of old bugs are fixed, and I'm sure we've added some new ones. So bear with us. So jumping into stall prediction. We've implemented a very simple-minded stall prediction methodology. It's based on this paper method for prediction of wing maximum lift. I basically use that. It's basically a model for calculating essentially, a bound on minimum pressure coefficient. I modified it to account for Reynolds number based on Carlson CP limit correlations. So it's a function of both local Mach number and local Reynolds number. And so it basically is a post-processing to the solution. So you run your solution at some Mach number and angle of attack. You'll get a lift drag and moment from that, as you always have. And if you have this model turned on, it will go basically along your wings and look at this model to basically identify places where it thinks that you've stalled the wing. And point out it really is only being applied to wings at this point. This is, like I said, it's a simple post-processing, so it really doesn't cost anything to apply it, so the solver doesn't run any slower. And if you're doing a Reynolds number sweep, like I said, this model is a function of both Reynolds number and local Mach number on the wing. So if you run a Mach number of 0.6 and an angle of attack of 15 degrees and do 20 different Reynolds numbers from low to high, it basically is just a post-processing at those different Reynolds numbers of that single invested solution that you're given Mach number and angle of attack. So it's very fast to use this model. It's not really going to cost you anything. It works for both the VOM and the panel modes of the solver. And just as a simple test case, I looked at the NASA EET configuration, picked out just basically looking at a clean configuration, the experimental data, it's about Mach 0.1, the Reynolds number about 1 million. So this is just the geometry for that EET configuration. So I'm just looking at the wing body, so I'm not modeling up the nacelles, and for this I'm just looking at the stall on the wing. So we didn't bother to model up the horizontal tail or the vertical tail either. So in VOM mode, that's just the Vortex Lattice model there down in the lower right. Ran it through a sweep of angle of attacks at that 0.1-ish Mach number and about 1 million Reynolds number. The purple curve there in the upper left corner is the CL versus angle of attack. And for the normal VSP solver, it doesn't know anything about stall. It's just going to chug along, so you can give it angles of attack of 15, 20, 25. You can run it at 45 if you wanted to. And for the most part, the lift is going to go up essentially linearly. There'll be some drop off just from the theory. Same thing if you look at the drag polar, right? It's, basically drags. This looks like a parabolic drag polar up at these, incredibly high CLs that are just not physical. If you turn on the CLNX model, and for this case anyway, it's doing a really good job of predicting that stall point. So again, it's just looking at the pressure coefficients on the wing and identifying a limit based on both the local Mach number and the local Reynolds number, and determining if, in a spanwise strip along the wing, if that section has stalled or not, and tries to estimate what percentage of that in the chordwise direction that section is stalled. And so if you look back there, the blue curve is the experimental data, and the green curve is the VSP solution post-processed with the COMAX stall model turned on. And it's doing probably better than it deserves to do for this geometry. And in the upper right-hand corner is just the polar, again, compared to the experimental data, which they took it out, to these really high angles of attack. And then in the lower left, surprisingly to me, it actually does a decent job of the pitching moment. So you see that stall, the pitching moment, it kicks up, vehicle basically goes unstable, CM alpha is positive at that point. And it actually captures that. Panel mode results are very much the same. A little bit more noise in terms of the drag pullers. But again, basically it doing a decent job of predicting the stall. A little bit over prediction in the CL in general from the panel code. That tends to be basically the vortex lattice method. You're getting 2 wrongs make a right. Vortex lattice method, you're ignoring thickness. You're also ignoring the boundary layer buildup along the wing, which is going to affect the CL. Panel mode actually has that thickness, but it doesn't have the boundary layer. So you tend on geometries like this to actually capture more of the CL that you should from an eviscid code, and then you would have to add in a boundary layer solution to actually get back to what the vortex lattice was giving you. That said, obviously from a panel code, you do get the upper and lower surface distributions of the pressure that you're missing from something as simple as a vortex lattice model. But again, in general, both the CL and CDs generally match up with the experiment, and you also capture that pitch up in the CM at the stall. So, structural analysis support. This was something that's been asked for quite a while, something I've been wanting to do for quite a while. And hopefully I'll get some questions on this. But basically, we have in OpenVSP, there's been a lot of work done to do basically the internal structural analysis or buildup of the structural analysis for both calculus and Nastran finite element models. So, you can go in and model your spars and your ribs and the skin and use the built-in mesh generation tools in OpenVSP to generate the models for either Nastran or the open source finite element solver calculus. What was missing in this whole path was a way to get VSPaero loads into either that Nastran or calculus model. So you would end up with a finite element model that basically had no loads in it. I mean, you could go in by hand and add in some loads. You could go in and add weights, things like that. But there was no easy way to map a VSPaero solution into either calculus or Nastran finite element model. For now, calculus is fully supported. It would be fairly easy to do Nastran. I just don't actually have anybody running Nastran right now that I could actually test out that whole process. But I don't expect it would be a big deal. It's basically a file format at this point. Both the panel solution and the models are supported. For the panel solver, we basically will map the surface pressures straight to the skin model that's coming out of OpenVSP for the finite element geometry. For the VLM models, you have this potato chip model, so we don't really have an upper and lower surface. What you have is a single potato chip surface and a delta pressure basically through those. And so what we've done is just basically split the difference. So we basically will apply half of that delta pressure to the upper wing surface and half to the lower surface, as we really don't know what that split is coming out of the vortex lattice code. But the net load would be mapped over, just half of it basically is going to be applied on the lower surface and half would be applied on the upper surface. The viewer for VSPaero has been updated, so you can view calculus input files, and then you can also view the calculus solution files. And again, it's basically down to file formats. There's no reason why we couldn't do this as well for the Nastran files in the future. So just as an example, grab the EET again. Just kind of went through a default setup. Not anything really to compare to here, but just trying to show the process. We've actually done a bunch of internal use of this on other geometries, and it generally is doing a really good job. compared to other codes using Nastran and higher fidelity CFD. So I modeled up the EET just looking at the wing. Basically skins, ribs, and spars were modeled. I don't know if who's going to talk about this in the workshop, but if you're interested in the details that the FEM modeling, I'm sure there's a slot for going over that this week. So you can view the calculus outputs now in viewer, just to make sure that everything's the way you expect them when they were written out to the file. You can obviously view these in OpenVSP already, but just the view of the skin, kind of the default mesh that came out, and the default mesh for the ribs and spars. Just with all the default materials, which are just some standard aluminum. So on that, just ran the wing alone. There's a typo there, supposed to be VSP arrow on the lower. That's just the panel solution. It's the CP contours. And then there's basically a tool now, it's called ADB to load, that will map that CP distribution over to the finite element surface. So I mean, these look like the same geometry, they are, but they're actually two different meshes. So the left one is the VSP geometry and mesh using the comp geom to generate it. On the right is the unstructured mesh generated in the finite element routines within OpenVSP. So we're mapping that across. The contour colors are different because just to point out that on VSP arrow is calculating the coefficient of pressure. The loads that go into calculus are in fact the pressures. So you'll have to define basically a dynamic pressure to do that conversion over from CP to actual pressures when you generate this load case and do the mapping. Once you've done that and you've set up a number of other things within calculus, all of which we've actually added in there, things to basically find like the symmetry plane points, add in boundary conditions so that your wing doesn't fly away when you apply a load and run it through the solver. There's a bunch of other things that we've done in there in general to allow you to tie multiple FEM models together. So we've done this with a strut braced wing where we had the wing and the strut and a brace all modeled up in OpenVSP, all modeled within the finite element tools within OpenVSP, and all had loads applied to them from VSP arrow, and then the structures tied together. So we have a number of different tools that we'll include here in the future to allow you to do all of that. And then within viewer, once you've run calculus, you can pull in that solution and take a look at the deflected geometry. So here we're just looking at the skin deflected on the left, just with the baseline, actually VSP arrow geometry there in gray as a reference. You can look at the actual deflections. You can look at the contours, in this case of the deflection magnitude. On the right is basically the same information, but here it's showing it for the ribs and spars. So it's a fairly easy process now, at least for a single wing, to go through and run VSP arrow. Once you've got your finite element geometry modeled up in OpenVSP, write that out, do the load mapping, and then run calculus. Presently, this is all had to be done on the command line, but I expect at some point this stuff will get rolled in, so you'll be able to do this all from the GUI. So optimization. I've shown some optimizations in the past. I've used it basically to kind of like show that the code is kind of doing what you expect, where I've done kind of a reverse optimization, taking a Hershey bar wing and optimizing it to minimize drag, and you'd expect basically to get back an elliptic loading. All that was done with finite difference methods. So, typically in optimization, you need to calculate gradients. You need to, if you try to minimize drag, you need the partial of drag with respect to, whatever your design variables are. And so if you had, 30 30 design variables, maybe those were the twist along your wing from root to chord. You'd have to run VSPro once to get the drag at your design condition, and then you would have to vary each one of those design variables individually, rerun VSPro 30 more times, and then use finite differences to calculate those gradients. And so just in that one case there, essentially to do one step costs you, over 30 times the solution time of a single VSPro run, just because you had 30 design variables and you had to run 31 solves to get all of the gradients that you're required. In addition to that, there's always round-off issues. Finite differences aren't exact, so you always have to decide, how much do you perturb each design variable to get a reasonable solution for those gradients out of using a finite difference process. And another way to do this is using what's called the adjoint formulation, and I'll go through that in a little bit in a minute. But the benefit of that is that essentially the cost of calculating those gradient calculations becomes independent of the number of design variables. Here we're applying the adjoint formulation to the actual mesh nodes. So the XYZ locations on your mesh are the actual design variables. So if you run VSPro, say in the vortex lattice mode, you might have, a mesh with, say 2,000 loops in it. So you would have on the order of, say, 2,000 nodes in your mesh. Assuming they all got agglomerated into quads. And so each node has an XYZ location, so you'd have on the order of, say, 6,000 design variables for a very simple way. So the process flow is basically you run VSPro to obtain a flow solution at some cost t. Depends on your geometry and, how many points you have to define that geometry. You would then run the adjoint solver to obtain the gradients of whatever objective function you're looking at. It might be CD, it might be CL, maybe you're trying to trim, maybe it's a combination of all of those. But you want the gradients of your objective function in respect to all the nodes in X, Y, and Z. In general, that's costing right now on the order of about 5t. So if it took, 5 seconds to run VSPro, it's going to take on the order of like 25 seconds, a half a minute to run the adjoint solver. You can then use chain rule to get the gradients with respect to any OpenVSP parameter, and I'll talk to that in a bit. Then you can feed your favorite optimizer, and then you repeat the process until you converge to some optimum solution. So can't go through a presentation without having some equations. So I just wanted to talk, kind of at a high level, what I mean about adjoints. So in general, you've got some residual function, and so we can just basically, we have some function R of gamma and X. Gamma is the solution vector. So for a vortex lattice method or the panel method, we basically have vorticity strengths, or it should be a gamma sub I on each panel. So that's a vector of vorticity that's distributed across the entire surface. And you've got some mesh defined by all these nodes X sub I. And you've got basically an equation at each vortex panel, which is basically the flow has to be tangent to that panel. So that gives you a linear system of equations, AX equals B. We can rewrite that as just AX minus B equals 0, or just at a higher level, R of gamma and X equals 0. So this is just a linear set of equations that fall out of either setting up a panel or vortex lattice solution. And then, for a fixed geometry, we have, J equals 1 to the m unknown values for the circulation, gamma J for each vortex panel. And then like I mentioned, you have the X sub I, which are basically your mesh nodes. And so there'll be a different number of nodes, not just m, in general, n nodes, define your geometry. And we can take the derivative of that residual function in respect to the mesh nodes X sub I and just use chain rule. Basically, you get the partial of R with respect to X plus the partial of R with respect to gamma times d gamma dx. that still equals 0. The original residual was 0, so the derivative equals 0. We can rearrange that, solve for dr dx. And we'll just note that that dr d gamma term there is the Jacobian matrix for this residual function r. Right, so this doesn't seem like it helped us any. We know that we basically want to calculate, basically the change in, the drag, for instance, with respect to the mesh, but we're kind of looking at what is the change in the residual with respect to x here. And we're showing it's just basically the partial of r respect to the gamma times d gamma dx. So this is just how much does your residual change if you change the solution vector gamma times how much does the solution vector gamma change if you change your mesh x sub I. We can also rearrange that basically to solve for d gamma dx, and that's just equal to the inverse of that Jacobian matrix times dr dx. So again, that doesn't seem like it helped us much, but let's go and look at, let's say we actually have some optimization problem we want to look at, and we want to minimize the vehicle drag coefficient, CD. And in general, it's going to be a function of the solution gamma and the mesh x sub I. And on top of this, let's say we have some set of OpenVSP parameters, p sub I, from 1 to n. So those might be the twists along the wing, or it could be the dihedral along the wing, the sweep along the wing. It could be anything that defines your geometry. I'm talking wings here, but it could be the cross-sectional radii of your fuselage. But these are, in general, these parameters that are driving your geometry in OpenVSP, and you've got some number of them. So we can take the derivative of CD with respect to the mesh, so dc dx. That's just, again, chain rule, kind of like we did for the residual. So you get partial CD with respect to x. So that's the change in the drag with respect to the mesh change. And then you got partial CD with respect to gamma times d gamma dx. And so that's just the change in the drag coefficient when you change the solution times the change in solution when you, respect to a change in the mesh. We can basically rearrange that where we can get rid of that d gamma dx because we solved for that previously when we looked at the derivative of dr dx. So we can replace that d gamma dx term on the right-hand side with the dr d gamma inverse times dr dx. And then we can rearrange things a little bit there, just combine the first two terms into a term, and we have that dr dx there. So now we have something that looks even more complicated than we started with at the top of this page. And I'm going to define that stuff basically in the brackets there as psi transpose. So psi is a vector, and so that whole thing inside the brackets, if you look at it, it's basically a vector times the inverse of the matrix. And so it's a vector, and we're going to call that psi transpose. So we've defined psi transpose, this, like I had there at the bottom of the page. And so if somehow we knew psi transpose, we could calculate psi transpose times dr dx, negate that and add it into partial CD with respect to x, and that gives you the total derivative that we started with at the top of the page. So that's the change in the drag with respect to the mesh. So the question is, can we calculate psi? So we can rearrange this, and basically, if you take the inverse of both sides and the transpose of both sides, do a little bit of algebra, you can come up with this equation for psi. So it's this dr d gamma, again, that's the Jacobian matrix, transpose times psi equals the partial of CD with respect to gamma transpose. So the right-hand side is the change in your drag with respect to the solution change. And the left-hand side matrix is just your Jacobian matrix transposed. So this whole thing is called the adjoint equation. And if you solve this, if you can formulate this and actually solve this for psi, it allows us to calculate the gradients of CD with respect to the mesh nodes x sub I. And so for the solving, a single system of equations basically gives you the solution for dc dx for gradients for every node. So the question is, can you solve this efficiently? And the answer, of course, is yes. And then you go back down. If we really care about the CD with respect to some OpenVSP parameter, we basically just use chain rules. So we have partial CD with respect to some parameter that you've got defined for your model in OpenVSP. That's just the partial CD with respect to x sub I, which is what we've been working towards solving here. So we know that, presuming we've solved this adjoint problem. And we just multiply that times the partial of x I respect to p. So that's that second term there, the dx di, dx of I respect to p. It's just a change in your geometry with respect to some parameter in the mesh. And you basically are doing this every day when you're playing around with OpenVSP and you're moving that slider around to change the span of your wing. That's basically, calculating on the fly the partial of span or of the wing geometry with respect to that span variable. So we can basically easily calculate the change in mesh with respect to your various parameters. We can store that, and then we basically do this inner product, this chain rule, to get dc dp. So the adjoint equation, it's linear. We can use automatic differentiation tools to help us set up that system of equations. I'm not going to go into that here today, but I'm basically making use of the adept C++ framework to do that. It turns out we can reuse pretty much all of the VSP solver framework to solve that linear equation. We then get the gradients with respect to any number of design variables for the cost of one VSP and one adjoint solve. And like I said, basically right now that adjoint solve is on the order of about 5 times the cost of a single VSP solve. So if you're just running, a single design variable, and that's not really an optimization, that's more of a trade study, but if you're just running a single design variable, wing twist at the root, then it would be faster just to do finite differences, all things being equal. If you're doing more than about 5 design variables, which is going to be the norm on most any real design problem, then this would be a break-even situation. And if you're doing more than that, then the adjoint process that we've put together here would be a time saving. So, and then there's a lot of work that is going to go into hopefully reducing that cost for the adjoint, probably down to something on the order of 2 times the cost is where I think it will end up being. There's a lot of, alpha beta-ish code in there now that all works, but isn't the cleanest. So the test case, just a simple wing, incompressible, Mach 0.01, 5 degrees angle of attack. Stuck the CG up there near the nose of the vehicle, so by definition, it doesn't trim. I'm running this in VLM mode. It will work for both VLM and for panel mode. Really, there's no difference in the setup or run, but just in the run times, it's just easier and faster to do VLM. Obviously, using the adjoint solver for the gradients. So the design variables, I have 9 sweep values along the span, 9 twist values along the span, 9 dihedral values along the span. So there are 27 design variables. So if you were doing this with finite differences, you would have to run the solver once at this Mach 01 and 5 degrees angle of attack, and then you would perturb all of those design variables one at a time and run 27 additional solutions for a total of 28 VSPO runs. Kind of per optimization step where you would need those gradients. I threw together just a simple Python-based conjugate gradient optimizer, and I'm just using a penalty formulation to basically minimize this functional here that I list out. So it's basically, CL minus some CL required, which was set to 0.5 squared, plus CM squared plus CD squared, and then A, B, and C are just these penalty function weights. So if let's say B and C were both 0, then your functional would just basically drive CL to CL required, and that would be the minimum of F. If you add in, a non-zero B, then now that CM squared term becomes into play, and the minimum is going to have to be, obviously, CM would go to 0. If C is non-zero, then again, you're going to try to minimize this functional. So now the value of CD comes to play, and obviously you're never going to get CD to go to 0 unless you drove CL to 0. And it was basically no twist, no dihedral, just a flat plate. So that CO was also 0. You're always going to have induced drag if you generate any CL. And since we're driving CL to 0.5, CD is never going to 0. So it's going to try to minimize that CD, try to drive CD down to 0 such that CM goes to 0 and CL goes to the 0.5 value. So the graphic there is just the initial solution on this SWEP kind of default one coming out of OpenVSP. We run this, ran it out. Basically, it's doing 9 iterations of the conjugate gradient solution. So it's evaluating the gradients 9 times. You can kind of see those in the steps there, where there's big steps and kind of like where the gradients are going on. It's a little less obvious in the later stages where things aren't changing as much. But the upper left corner is just the value of sweep. Then upper right's dihedral, which isn't changing a whole lot, and then twist. And so what you end up with is, basically this goal-shaped wing. It's trying to trim this vehicle, and in the initial guess at your geometry, the CG was at the apex of the wing, and so all of the lift was behind the CG. The only way it can actually really kind of twist is a sharp moving lift forward and then adjust the twist along the span. So it does that. And it also does, play around with both the twist and the dihedral because it's trying to minimize that induced drag. Just looking at the loading, which is the upper left corner, the baseline loading there is in purple, and then the optimized loading is shown in green. So it's kind of loading up the roots, unloading the tips. Just the CL history there along the functional evaluations. So it quickly, it's starting down there at CL of around 0.44-ish. It's trying to drive that up to 0.5. The CD one, it's not really trying to drive it to anything. It's trying to keep it minimum, but it's increasing the drag. The CD is going to go up in general, but it's trying to keep that at a minimum as much as it can. And then CM hasn't quite driven it to 0 here. It's a trade-off between all the other weights there in the penalty function. I basically put a much larger weight on CL versus CM. If you played around with those weights, you could trade off, on CM or CL. I'll let this play a little bit here. So this is just kind of an animation of the optimization process. So within Viewer, you can load in all of the intermediate solutions during the optimization process, at least as I've coded them up for my simple Python script, which we can include in the distribution in the future. Just kind of showing what it's doing. So initially it really goes after, that sweep. Then if you look at, the tips, it's playing around with both the dihedral and with the twist. And so, this is not meant to be like the end all in terms of optimizers. I just wrote a very simple conjugate gradient optimizer in Python. There's obviously a lot of other much, better optimizers out there. This whole development, this code is actually being pulled into NASA's OpenMDAO framework, which I don't know if anybody's gonna talk about that this week, but OpenMDAO is also open source. It allows you to tie together, any number of models in a framework that allows you to do optimization. And so in that framework, one of the optimizers that they have is SNOpt. So this has been pulled into that framework, and where they have I'll call a real optimizer where you can actually do optimization with constraints, and not just some simple penalty formulation like I've done here. But the focus here on this discussion really should be on the gradient calculations and how that's benefiting from the adjoint formulation. So there's some notes on this. This ran in like 3 minutes on my laptop. It was like 45 seconds for all of the adjoint gradient solves. There were 9 gradient solves for this solution here. It's about 20 seconds for all the solver solves. There was like about 65 individual solver solves in this process. So that's 65 seconds. So like a third of the time was actually VSP. The other 2/3 of the time were spent in my probably not very well written Python code. I just used default Python lists and everything, so I'm sure I could get all that basically down to a fraction of that remaining 2 minutes, the way I coded it. But that really wasn't the point here. But just looking at the adjoint solves themselves for calculating the gradients, for this case where you've got 27 design variables, it's essentially almost 2 times faster than using finite differences would be for this case. If you just look at what the cost of an individual VSP solve is and then multiplying that by 27. So already in this case where you've got on the order of 30 design variables, it's faster. And my expectation is that this will get faster in the future once we go in and optimize the code. Okay. So my final topic, and I think we're doing okay here in time, things that go round and round. So right now there's kind of 2 ways, or I should, in the past, there were 2 ways to model rotors in VSP. The actuator disk model, and it was fast. It's really developed for propellers, not for rotors. And it really doesn't work for edgewise flow. I mean, you can run it for edgewise flow, and if you're, not totally on an edgewise, then maybe you'll get a reasonable answer out of it. But it really, the theory really was not developed for edgewise rotor type flows. It's based on basically flow coming in normal to the actuator disk, and so anything even at a slight angle of attack really is kind of breaking the assumptions in the underlying theory that went into that model. The other way that you could model rotors was the unsteady analysis. It's not so fast, at least compared to just a single steady state solution. But it works for propellers, it works for rotors, it works for those in combination with wings and bodies. So it's fairly general, and within the framework and theory of the vortex lattice of the panel methods, it seems to do a decent job. But it is expensive compared to running a single VSP solution, say with an actuator disk. So like bicycles, more is always better. So I've implemented a third way. Basically, I'm calling it the quasi-unsteady model for rotors. So the rotors are modeled, not actuator disks. So you go in there and actually use the prop geometry that's in OpenVSP. Those will be taken in, and VSP generates a guess at the helical wake shape. That's based on basically your free stream velocity, the RPM of the rotor, and the local angle of attack of the vehicle. The rotors and their wakes think they are rotating. The rest of the vehicle doesn't. So there's some magic going in there. And but let's just say that when the influences of the rotors and when the updates of the wakes occurred, they think they are rotating, while the rest of the geometry clearly isn't. Wake shape is iterated on to account for all the wing body interactions, just like you would have normal if you had wings and bodies. and wakes coming off of them. Wake-wake interactions, including in self-induced flow. So the wakes of the rotors interact with wakes of other rotors, interact with their own rotor wakes, and and all those wakes from wings and other rotors interact with them. However, the wakes are constrained to move in the thrust and free stream directions. So the updates occur, and then there's a projection process that goes to basically constrain the motion of those wake updates to move in what I'm calling the thrust direction and the free stream direction. So the thrust direction that's basically defined by the normal of, if you want to think of an actuator disc, but the normal to the thrust plane. And the free stream direction, which is just defined by, the angle of attack and the side slip angle. It's slower than the actuator disc model, but it's a lot faster than time accurate model. And you can apply it for edgewise flows, i.e. rotors can be modeled. Only question is it useful? So as a test case, and I'll just note this is all kind of early work in progress, but it is going to roll out. And so, we need to do more validation on this, but I've convinced myself it's a path worth going down at this point. So this is just a Mach 0.01, 0 degrees angle attack, Hershey bar wing, span of 40, aspect ratio 4. It's at 10 degrees angle of attack. I've just yanked in 2 default propellers out of OpenVSP. They're at plus or minus 10 in the span, running at 860 RPM. You can blame Rob for that number and Uber. The solutions were done. I just ran the wing alone, so you can see a comparison of what the loading and the forces look like on the wing alone. Wing plus the actuator disc model, the quasi-steady, and then the time accurate. So the time accurate solution here is shown on the left, and then we're just looking at the CP distribution, well, really the delta CP on the wing and the wakes. The wakes on the right for the quasi-steady look a little bit different, obviously. It's, but in general, there's an interaction between both the wakes of the wing and the wakes of the rotor. But you don't see exactly the same kind of, interference that you would see on the unsteady. There are fewer wake lines coming off the quasi-steady. I've been playing around with, just how many points along the span of the rotor blade do you need for these quasi-steady? And in general, I found it's less than you'd want to run for the time accurate solution, in terms of that pain benefit trade-off. So the wing CL distribution. So the wing alone is shown in blue. The wing plus the actuator disc is kind of that burnt orange color there. The unsteady average solution, so this is the unsteady solution on the wing averaged over the last rotor rotation, is shown in green. And I'll just note to begin with that it's quite a bit different than the actual rotor disc, the actuator disc solution. And then the quasi-steady solution there is in purple. And so, none of these solutions actually lie on top of each other, but in general, the quasi-steady is doing a reasonable job of capturing kind of the general shape of the unsteady average solution, which again is an unsteady average. So if you were to plot this as a function of time, you'd see this loading, changing quite a bit, as the rotor rotated and the various trailing wakes interacted with the wing. Looking at this, you'd basically say that the actuator disc is doing a horrible job. But then if you actually look at, the forces and moments here, so the unsteady forces and moments are on the top line. The next line is the quasi-unsteady, and then the actuator disc and the wing alone. And it's worth looking at, that top line and the bottom line. You look at the wing alone, the axial force and say, the Y force, but really that axial force and again, this is not drag, this is CX, is negative. So the sign changes just when you add in, that rotor, whether you model it as an actuator disc or full unsteady or quasi unsteady. The unsteady and quasi-steady, unsteady, in terms of CX, CY, and CZ all do a very reasonable, I'd say the quasi-steady is doing a very reasonable job of getting the forces. In terms of pitching moments, the same thing is true. It's notable that, in pitching, you look at CMY, that basically there's this reduction in pitching moment that's shown for the unsteady and quasi-unsteady, at least in an average sense for the unsteady. You see that with the quasi-steady. The actuator disc actually it shows it going in the other direction compared to the wing alone. And then CMZ, right, which is this yawing moment, is 0 for the wing alone. All the methods actually do a reasonable job of predicting this if you're just comparing this to wing alone. The quasi-steady, unsteady is ever so slightly maybe better. But, I would say, is this, exactly reproducing the unsteady solution? No. Is it useful? I think yes. So the solution times, and this is kind of where, why I say it's useful. Solution time, 6 rotations. It's about, 1,500 seconds on my laptop, just chugging away. The quasi unsteady runs in like 11 seconds. The actuator disc, 6 seconds. The queen wing, 1 second. So there is more cost there to, this quasi steady method compared to just running a queen wing or the actuator disc. But it's literally like 2 orders of magnitude faster than the unsteady. Rotating those rotors, 90 degrees. So you basically have edgewise flow. Everything is changed. It's the same except for the location and orientation of those rotors. Time accurate solution there on the left. The quasi steady state solution on the right. This one actually does have a similar number of resolution in the spanwise direction on the rotors for both models. There's obviously a lot more interaction going on the right, for the time accurate solution between the wakes. But you still, if you look at it, you can kind of convince yourself you're capturing some of that in the quasi-steady solution. And if we look at the wing CL distribution, so the wing alone again is in blue. The actuator disc is in that burnt orange, and it's just wrong. I mean, the method just really isn't meant to do edgewise flow, and the solution you're getting out of it is just wrong. There are some games you could play to maybe get something better, but really the model is just not meant for edgewise flow. The unsteady average solution there in green, and the quasi-steady in purple. Do they lie on top of each other? No. But I think, you're getting, some of you're seeing the delta, the impacts of this rotor on the wing. And so the question is, for the amount of time you put in, is this information useful to your design process? I think it can be. If you look at the wing forces and moments, we don't do quite as good as we did for the propeller case, but we're clearly doing a heck of a lot better than we did with the actuator. So the CX and CYs and CZs, they're within 30 to 50% of the actual values. But I think you need to look at those as deltas from the wing alone to understand that if you're looking for trends, which I think at this level of analysis and then this level of conceptual design is probably what you're looking for. I think it actually provides you some very useful information. And specifically something like CMY, the trim, it's acting in the right direction. So it's definitely showing the impact of those rotors on the wing in terms of trim, as well as in terms of the forces. So solution times, about 20 seconds on my laptop, 6 rotations of the blades, about 73 seconds for the quasi unsteady. I should say that these take more than the typical 3-ish wake iterations. I'm running these out typically on the order of 10 to 15 wake iterations to get the solution settled down. That's going to be very much geometry dependent. But it's kind of like running, high risk cases in VSPO where you've got, flaps and whatnot modeled. There's a lot of wake interactions going on, and you need to run out enough wake iterations to get that to settle down. Actuator disk, it took 5 seconds, but the answer was just point out wrong. And obviously the queen wing, it's on the order of a second again. But obviously that doesn't give you any information about what's going on in this configuration. Last one, this is kind of more of a gratuitous graphic. This is the Uber geometry. Time accurate solutions on the left, quasi steady on the right. Again, you getting all the interactions between the blades. So if you stare at it and squint, you can see that you're capturing some of these interactions that are going between the blades as well as the wing, wakes. From a load standpoint, this is like by far the worst solution you've seen today in terms of comparisons. You've got the unsteady average up the top, the wing low near the bottom, quasi steady is kind of splitting the difference. But if you look at the integrated force and moments, we don't do bad. You look at CX and CY, CZ, all the trends are actually there, and they're actually fairly close. CZ is off by 50% maybe. CMY, which is probably the big one in terms of trimming the vehicle and trying to understand the impact of rotor RPMs and how are you going to trim this vehicle, actually scarily good, probably better than it deserves to be. And again, you want to compare these all to the wing alone solutions. So CM is it's pitching down and it's pitching up, right? Obviously, these are just the forces and moments on the wing. These would be traded off with the thrust and the forces that are occurring, with the delta pitching moment caused by the thrust. So you trim this vehicle out with the rotors. So that Uber case, 12 rotations. I really ran that one out. It was like 5.5 hours on my laptop, and the quasi steady was 7 minutes. Right. So I think for what you're getting from the quasi steady solution, the trade-off in time is quite worth it. So what's next? I'm going to quickly go over this. I only have a couple minutes. Improvements to the joint. Most of it is basically trying to speed things up. It's a single processor right now, so I'm going to try to figure out how to do multi-processor. There's a bunch of wasted CPU cycles where things are basically being recalculated, reprocessed multiple times, and trying to improve memory usage overall in the adjoint calculation. Structural analysis, including both wings and bodies in the future. I should add in here Nastran. We definitely want to put that in. We're looking at trying to do some coupled solution process. Probably going to go down the mode shape path. Ultimately, I'd like to be able to do some flutter analysis. And then the quasi unsteady, like I said, this is kind of like work in progress. This is something that's been going on the last couple months. There's additional things that we could do to relax the rotor wake, iteration, shape relaxation. I'd like to tie this in with the noise prediction so that we can do kind of a quasi-steady state noise prediction. And then obviously one of the big ones that we want to do this is basically trim the vehicle using RPM and or generating rotor control type derivatives. All right, I think I got it.
Well, Dave, thanks a lot. That is an incredibly impressive amount of stuff. You've clearly been very, very busy. And, most of this stuff has not been released yet and hasn't even made it to me yet. So Hopefully these things will be becoming mainstream over the next few months. That'll be really exciting to see. While Brandon queues himself up, I think you can safely stop sharing your screen. While Brandon queues up for the next one, we've had a bunch of questions. Brandon answered some of them, but I'd like to just take a minute to have you answer some of the questions from the forum. Let's just, and some of these Brandon answered, but I'm gonna ask you again. So first, what does the CLMax variable do in the input file? Is it still supported given the new stall prediction tool? What should you set that to if you're using the new stall predictor?
Yeah, if I turn my camera on, you'll just see my dog. So it's if you're running it, editing the .vsp file by hand, if you set it CLMax to -999, it will kick in the new CLMax.
Okay, so CLMax -999. Okay, and otherwise it operates the way it always did.
Yep.
Great. Let's see. Would you give an answer just a little bit about the logic of when is a dgen geom file used, when is a VSP geom file used, and when is a try file used, and how does it pick?
Yeah. So it depends on what's in the directory, and I'm going off by the top of my head, so it's probably wrong. But if you have what it should be doing is if you've got a VSP job, it should take that first. Whether or not that's and I know Rob's going to talk about for the VSP job, that could actually be either a Vortex Lattice model or it could be a panel model, but it should grab that first. If it doesn't find that, then it should look for a try file and load that in. If it doesn't find that, then it should look for basically the CSV file for the dgen geom. And so that is essentially the order. For the panel solves, it will also look and see if there is a CSV file sitting around, but I think there it assumes that there's an underscore dgen geom tied to it. And it would try to pull from that CSV file things like the rotor, rotor prop locations, things like that, stuff that's not in the try file, and not in the VSP geom file, but were in the CSV file.
So yeah, thank you, Dave. I'll add to that answer and just say that the GUI tries to make that invisible to the user so that when you choose you use the experimental file format. And if you use the experimental file format, then it's going to choose to use the new VSP geom file. In general, I'd say for panel runs, there's no reason not to use the VSP geom file. It ought to work pretty well. The thing to check when you look at it in Viewer is if it captured the entire wake correctly. There might still be some problems where, at the very root of your wing or at the very tip of your wing, there's a part where there was a wake that did not get attached. And if so, share that test case on the VSP group, on the Google group with me, and I'll try and get it fixed. The experimental file format does theoretically work with VLM files, but it's much more experimental right now, in that we're still working through how that intersection works and whether those files are intersected or not intersected. So there's a difference in how those are handled. What this whole thing, and we will talk about this a little bit later in some of the other talks, the direction that Dave and I are driving towards is, a unified run mode where we always use the VSP geom file, and where you choose individually on a essentially a component by component basis, whether that component has a thick surface like a panel representation, or a thin surface like a VLM representation. The idea being that wings, vertical tails, horizontal tails, and rotors, any sort of lifting surface, you would most likely model with a thin surface potato chip VLM style representation. And all, bodies, pods, big fat things that don't lift, you would model with a thick surface representation. And then we actually have the ability now to trim those mixed geometries of thin and thick surfaces. So we would have all the benefits that Dave was talking about, where VLM does just an amazingly good job with lifting surfaces, but we would also get some of the blockage modeling from the thick surfaces. So that's where we're headed, but that's still probably a few versions from completion. There's a question: can the convergence tolerance be specified in VSP Aero?
No. Well, it's open source, so technically yes, but no. I mean, there's basically, it's converging. It's trying to drop the residuals by one order of magnitude. If you're doing the default, which is like 3 wake iterations, it will drop. During each iteration, it drops that residual one order of magnitude. So in actuality, you're dropping the total residual by 3 orders of magnitude. If you want, if you look at that way from, solving the equation, if you were to fix the wakes. And that's why if you actually set number of wake iterations to 0, it will drive it, I think in the current version, 3 orders of magnitude. I think I've relaxed that to 2 orders of magnitude. And then the second one is that there's a constraint on the maximum, the maximum residual. That usually doesn't kick in for well-behaved geometries, at least for the vortex lattice. I've done some tweaking in the version that Rob will be getting for panel solves that tries to do a more intelligent choice of that value to still get good solutions that, with a reduced number of iterations. But yeah, it's not a user input on the file. I would say for the VSP Geom stuff, all the adjoint gradient work was done using VSP Geom vortex lattice mode. And like Rob said, that's where we're going. And that's like, if you want to do optimization right now, you would have to write out everything with VSP Geom.
Cool. Has anybody applied the new stalled method to a powered lift case like the X57?
Not to my knowledge.
Okay. Someone noticed we've got the stability method that'll run, at least 7 cases and perturb all the different parameters and do stability and control derivatives. But often they just want to find the aerodynamic center and the static margin, which they can do manually. But is there any plan to have an automatic aerodynamic center estimate that doesn't do anything else? And are the adjoints going to play into the derivative estimation?
I mean, it would be easy enough to add that in. So if somebody reminds me, I'll add it in as a stab option, if that's what people want. I would not see using the adjoint to do that, or any of the stability derivatives and stuff. I mean, we could, but it's pretty fast the way it is already. So I think it would end up being a wash for most cases. But I mean, I've thought about it.
Okay.
But you start adding up all the derivatives and everything. I think even with the number of derivatives we have to do stab and control, maybe if you did control surfaces, maybe it'd be worth it. So maybe it's worth looking there at the adjoint formulation.
I'll just have one last question. If you would talk a little bit about supersonics with VSP Aero, someone was asking about it on YouTube, and if anybody done at Concord, how's the supersonics looking in VSP Aero? There's a whole presentation on the wave drag tool, but is just your comments on supersonic capability, and then Brandon can go.
Yeah, I mean, like I said, look at the previous year workshop presentation. I talk about the supersonic stuff there in more detail, but it really only works for the vortex lattice. So you're not going to get thickness effects or anything like that in terms of like, trying to get the pressure distribution. So I know I've had a lot of people ping me on trying to do things like predicting sonic boom and stuff like that. I mean, you can get the load distribution, the lift distribution from the vortex lattice, um, but nothing has changed over the last year in terms of that. I mean, I've had some discussions with various people on, extending the panel solver to supersonic, but that just hasn't happened, and I don't have any time frame when that might happen.
Thanks so much, Dave. Really appreciate the talk.
Yep. Thanks, Dave. That was quite a lot of material to cover in just the hour that we gave you. So thank you again. And in that same vein, for those of you that are either relatively new to OpenVSP and VSP Aero, haven't had a lot of time to play with it, or you're just getting started, and even for some of our more seasoned users that might need a refresher on some best practices for the tool itself. We're going to cover some of that and go into general guidance and guidance for panel mode, VLM specific, some things that you can do to try and troubleshoot. So with that, let's go ahead and get started. So again, we're just going to go through some of these bullet points, talk about a few things, but I want you to keep in mind that these are guidelines as a starting point. It's not necessarily comprehensive. Different models are going to have different behaviors. There are going to be certain things that will either work or break depending on how complex your aerodynamic model is. So the refinement is really up to you, but this should get you a good place to start. As a reminder for everyone on the line, I know I kind of breezed through my introduction, but again, I'm Brandon Litherland from NASA Langley in the Aeronautics Systems Analysis branch. And so the first thing, and probably the last thing that I'm going to say as a part of this presentation, is use a build-up approach. So you want to start simple, and kind of like Rob mentioned at the very beginning of the workshop, it's think about what it is you're trying to find out. Think about a free body diagram, what really matters in the type of problem you're trying to solve. So if you only want the lift on, say, a wing, all you really need is the wing in isolation. It's doing almost all of the work for you. But if you want to try and get to something like a trim solution or try and account for the moments, then you probably need a tail. So you add additional geometry to the model as you build up in complexity. And here we've got, the outline of the common research model for the X57, and this one's the simple version that just has actuator discs. Under no circumstances should you be starting with this. If you load this model up and just hit go on VSP Aero, it's going to crash, and it's still a relatively complex thing to set up, and you might not know why it broke. We'll get into some of the why in this presentation. So the idea here is to build trust in your model and your methods. So if you have experimental data, great, compare to that and try and calibrate everything to it. Or you can compare to a similar model. So you should be able to see, if something is coming out the way that you would expect. And then you can also look at the trends in your results. So you know that, say, VSP Aero is typically an inviscid potential method. So as Dave mentioned, the lift curve is just going to keep climbing until you go up, past a sine 2 alpha, and it's going to start coming back down. So keep in mind the assumptions and the limitations of both the solver and the things that are in your model. And then you can gradually increase your complexity. So if you happen to add something and it doesn't behave the way that you expected it to, why? Is there some feature in what you added that broke it? Or is there something going on in the wakes to where it's being hit by something? Or is there some other aerodynamic part of the model that's impinging on this other thing? So if you start out with a wing and then you add things like tails or control surfaces or propulsion or bodies to it, there is an increasing complexity where you can either just have, say, a simple wing, you can have subsurfaces, you can have separate components, you can do actuator discs or rotating blades. There's lots of stuff that you can do. So again, if VSP Aero isn't working, it's returning a not a number, it's giving you weird results, take away everything but the wing and then try again. Add one thing at a time until things break, and then why did it break? Try and figure out what it was about that completely screwed up the model. And in some of these slides, you'll be able to find out some of the things that you should be looking for when you query your model. So as some general best practice, you can use clustering to your advantage to try and improve the solution, or at least give the solver a way to calculate information where stuff is happening. So for example, you can give it more points out at a wingtip where you're going to have a larger drop off in the lift curve. And that's typically going to give you a more accurate solution than if you just left everything in a uniform spacing. And if you have a lot of points, it's probably going to give you a decent lift curve, but it's going to cost more time. In this way, you're giving it fewer nodes as compared to a completely uniform solution, but you're still capturing information out at the tip. So for a single section wing, you can use a root gradient or root strength of say 1 or 2, and out at the tip, something like 0.2 to 0.25 is pretty typical, where you can get some more information out at the wingtip. For a multi-section wing, however, you can set the clustering near section breaks so that neighboring cells are similar. You don't want to have, the end of section 1 with a bunch of tiny high aspect ratio sliver cells and then have it jump like 2 feet. And those two side by side aren't really going to like each other very much. So you can set these reasonably close together, add a little bit more cell density behind something like a propeller, so that, again, where all the interesting stuff is happening on the wing, the solver has enough density in the panels to where it can capture those effects. And another thing to keep in mind here is that more points doesn't always mean a better solution. So in the examples here, we've got versions A, B, C, and D of the same wing, where we've got, say, the default setup where we've got 33 and 6, 6 being in the spanwise direction, including the root and the tip. And then we kind of bump it up a little bit as we go. And you can see in the VSP Aero solution that, solution A has most of it, but it's not quite right. And by the time we get here to where we have 41 points around the chord, 21 points in the span, we've pretty much captured it, right? And so going all the way up to 61, 61 didn't really gain us anything, but it cost us some time. And for something like this, where we're at 201 chord-wise points and, really dense spacing, this is overkill for VSP Aero. You don't need to do this. Something this accurate would be a really great place to start if you need to mesh up and go out to something that's a higher order RAND solver in CFD, for example. But VSP Aero isn't going to like this. And in fact, the cells can become so small that they start to cause problems in the solution. Similarly, you'd like to avoid any high aspect ratio slivers. So in this case, we've got, say, 6 spanwise and a whole lot in the chord's Y direction to where we've got these tiny little high aspect ratio cells. And conversely here, we've only got, say, 17 in the chord-wise, but I think this is like 61. And it makes these tiny little slivers out here. And that's going to cause you some problems. So try and avoid that. So let's focus in a bit on vortex lattice mode. And sometimes what we see, particularly in the VSP Google group, is that people will throw a vortex lattice solution at something and they'll have nacelles, they'll have body components, they'll have all sorts of things included in the model. And really, the bodies aren't contributing anything to the lift or drag because they don't have wakes. So they're not really going to contribute at all to the lift or drag, but the body cruciforms do have an effect on the total moments. But these have to be used wisely, because if there are any local interactions or local intersections with, say, the vortex lattice panels and the cruciform, you can cause problems for yourself where the local interactions start to affect your solution. So you can try and avoid this by checking your degenerate surfaces and watch out for overlapping panels by using that camber degen surface representation mode. Some other things that you want to try and avoid are things like coincident surfaces. So if you have overlapping wings or body cruciforms that are right on top of each other. So you can see, where'd my mouse go? Here we go. You can see some overlap here between the vertical tail and that vertical cruciform that goes into the body of the fuselage. And probably one of, if not the most common issue that we see in vortex lattice mode is rounded rectangle. Because there are these straight sides on the side of the section itself. Whenever the vortex lattice tries to collapse down into that potato chip surface, all of those points get collapsed into a single point. There's no distance between them and it throws an error. So if you try and run, you've got your fuselage on, you're using rounded rectangle, and the first thing it does is says not a number and crashes, that's probably why. What you can do is replace these sections with ellipses. So the vortex lattice fuselage is going to look exactly the same regardless of the cross-section type that you have. It's using height and width and building it up. Ellipses will work better for this, and for the contributions of your moments that you're trying to capture, if you're including bodies, the ellipse will work just fine. This also goes for things like body sections with vertical faces and closures. So if you're trying to have, say, a stack or some fuselage component where the DX is 0 or the location of the cross sections are right on top of each other, it will do the same thing. They'll try and smash it down to a single point and you'll have a failure. But even a very small offset of these distances, for example, if I'm working in feet, something like 0.02, is more than enough to make sure that these crashes don't happen and it will run just fine. And for VLM wings in particular, when you have control of, say, leading edge and trailing edge clustering, use about 0.25 at the leading edge, 0.25 at the trailing edge, and that's typically accepted good clustering of points at the leading and trailing edge for the VLM mode. Moving on to discuss panel mode, you'll notice that you can't use blunt trailing edges on wings or bodies. But what you can do to try and help this along is to change native blunt edges to a sharp edge using something like closure or caps. So you can sharpen the aft-facing body surfaces by either adjusting coincident sections slightly, so that's more of what we were talking about with that nacelle. Just shift those sections a little bit, and then you should be fine. And when we're talking about clustering values, for panel mode, it's usually better to do, say, 0.25 or even 0.2 at the leading edge, and leave the trailing edge value at 1. So you have some nice distance between the closing section and then the next one over it. It has a nice sharp edge to attach a wake to. And with the images here, we're looking at a few different ways that you can adjust the airfoil. So the flat cap that you see is going to cause failure when you try and run VSP Aero. But if you put an edge cap on there, it extends it very slightly. It doesn't really affect the chord length, even though it does just a little bit, but it will run just fine, and you still maintain the upper and lower cambers, upper and lower surfaces of your airfoil. If you're using closure, you can use skew both, or you can maintain, say, the upper surface distribution by skewing the bottom, but you want to set that to 0. And if you skew both, the camber line's maintained. If you skew, again, the bottom, it's going to bring the bottom surface up, but the top surface is going to be effectively unchanged. It's kind of up to you how you apply that. And something to keep in mind that airfoils are not all equal. You need to pick which one of these methods works best for you. So you can do something like set closure and set extrapolate and go to 0, but if you do that, it's going to take the tangencies on the top and bottom surface and loft it out to a point that's going to significantly extend your chord, and it's not really recommended that you do that. So another thing that you kind of want to watch out for is with subsurfaces in panel mode. You can inadvertently put the edges or the bounds of a subsurface right on top of these interpolated sections. And you can see those right here and here. And in the solution on the right, you can see that this kind of made some hot spots where all of these were joined back together. There wasn't anything necessarily wrong with that, but you can see that these peak values where it's coming up with some of this are really, really large. So that tells you that something is wrong. If you adjust it a little bit, then you'll see that those peak values come down. So incidentally, that's one of the things that you can use Viewer for to try and identify if there's something wrong with the model. Another thing to watch out for with panel mode is to avoid intersections that cause bad triangulation. So you can see that when we first tried to put this little glove and bat region together, there are some little slivers that are poking through where the intersection had a hard time putting the triangles and figuring out where the intersection was, because these were exactly coincident surfaces. And when you try and run that, of course, you get not a number and it fails. But if we shorten the tip chord, decrease the thickness out here, give it some taper, and have a well-defined region of intersection here, all of this comes together nicely. It's got a good intersection curve, and this will run in panel mode just fine. And there's a bit of an issue with actuator disks in panel mode. I've tried recently to try and add it through the GUI. You can add them in by modifying the input file yourself and then running VSP Aero from the command line. This is just a bug. And like Dave said, sometimes when we make new and interesting things, some bugs are introduced. So it's just something that'll be fixed here soon. But you can see here that you can add actuator disk to panel mode. You get the blowing over the wing. The wakes are behaving relatively normal. And this is that same model I just showed that has the good intersection. So you can see that there's kind of a nice pressure distribution here from the fuselage down through the glove and back onto the wing. And you'll also notice that if you grid up something with comp geom or you're running panel mode and it's failing, and it shouldn't because all of the intersections are nice and clean, try and turn on the experimental file format. And because it's not necessarily trying to find any hybrid lifting surfaces, it's all panel tries, it's going to run the VSP geom and panel mode will end up working. Not quite sure why exactly that happens right now. It's more something that we're digging into, but just in case panel fails and you know that it should run, try VSP geom by turning on this experimental file format button in version 3.25. Moving on to actuator disks, and in the interest of time to try and make sure that we get to our next by 2 o'clock, I'm just going to hit some of these points and we're going to continue on. So there are a couple of ways to use actuator disks in OpenVSP. One of them is the disk custom component that's packaged with OpenVSP, and the other way is to use a prop. So in the GUI, if you're using just a disk, it doesn't really have the pointing vector to tell you which way it's oriented. So if you rotate in -y 90 degrees versus +y in 90 degrees, the disk doesn't tell you which way it's pointing. Propellers have the thrust vector built in, and then when you're ready to run something like, say, actuator disk mode, you can go to the design tab, switch from blades to disk, and then VSP Aero, at least in the GUI, is going to read all of those in and automatically have the hub diameter set according to your R0 value for the prop. If you really want to use disks and don't feel like using the prop component, a really simple way is to attach a blank in to the component in both translation and rotation, and then the X direction is always going to be the direction that it's blowing. So that helps you keep your orientation. When you're trying to figure out your thrust and power coefficient for a disk, these are defined basically according to these equations. So it's the thrust over the density, the revolutions per second squared, and the diameter to the fourth for thrust, and then the same thing for power, except you've got n cubed d to the fifth. And these are related using the advance ratio here. So it's CT times V over ND will give you your power coefficient. So if you either know how much thrust you need and you know your advance ratio, you can get an estimate of power coefficient. Or if you know how much shaft power is going into a propeller and you know the advance ratio, you can back out how much thrust it should have. There are other ways, and perhaps more rigorous or detailed ways of computing these, namely things like X-rotor, which you can get from the MIT source page. You can look up Hamilton Standard Redbook Max, so things like HS Prop, which I don't know if Rob has that open or not. There's your own blade element momentum methods if you happen to have coded up your own. And you can even pull open the propeller performance from manufacturers using things like performance tables. And when it comes to modeling things like rotating blades, just leave the prop in blade mode. Dave went over this a little bit, but treat the blades like any other vortex lattice or panel surface. Use the same guidance for clustering and tessellation. This example on the right is the X57 cruise prop that's been released as part of the Common Research Model. This is way too many points for trying to run this propeller. I think there's like 100 or something, or 80 in the blade-wise direction here. So again, use few points in chord and the blade radius, and chances are you're going to get a reasonable solution out of this. When you're trying to do this, try not to let them hit anything. So if you have the root buried down in a nacelle, try not to include the nacelle at first. If you can avoid it, just make sure that things run, and then again, build up, add complexity. And something that you'll notice is don't set unrealistic RPMs for props. If you have a helicopter and the rotor diameter is something like 40 feet, don't set the RPM to, 4,000. That's kind of a ridiculous value for something like that. The solution's going to blow up. You'll see the wakes turn into tumbleweeds if it finishes at all. So for propellers, we typically recommend starting with auto time stepping. And then if you need to kind of refine your time step or the number of steps, you can do that after you get it working. So we're here at 2 o'clock. I've got just a little bit to go through here, and then we'll roll into VSP Aero demonstrations. But I want to give you guys some tools that you can use to troubleshoot. And Viewer is really great for this. So the idea here is you open up Viewer and you take a look at something like the pressure distribution. And you're looking for things like large peaks. You can check the legend to see what those extreme values are, both in, say, the upper and the lower value. If you see things that are completely unreasonable here, it tells you that there is some cell involved in the solution that's causing problems, and you need to take a look at it. You can also look at the wakes and see if you're seeing the roll-up move as expected, if you're seeing, say, control surface deflections cause the wakes to dip down like they should. And even if something is missing, if you intended to have a tail in the model and then you pop in and for whatever reason the set didn't include that component and your moments look wrong, check the viewer. Make sure all of the components that you intended to run with are actually in the solution. Something that can occasionally get brought up is people will look at the viewer and say, well, why do my control surfaces look like they're in a completely different spot than what I prescribed? And that's mostly because this is for visualization only. The actual control surface deflection is being applied back here, and the deflection itself is just visualization. You can see the outline of the surface here in black, but a little bit of that panel ahead of it is being rotated with it, and that's okay. It doesn't mean that all of this was included. It's there to show you where it's moving. And you can always check the results manager. So does the span-wise loading make sense? Are there peaks? Are there little drop-offs? Are there places where everything is, failing? And then, just find areas that will help you identify whether or not the solution looks good. And you can always check the convergence. So if you click on that convergence tab, look at not just the L over D log residual, look at CL by itself, look at CDI by itself. And keep in mind that right now, 10 to the minus 5 is the minimum for log residual. And that's, 5 orders of magnitude. And you'll notice that if you get down to minus 5 and it just flatlines, that's as far as it's going to go. That's a good solution for VSP Aero. It's done. So sometimes you'll run, say, like 40 wake iterations, and by the third one, it's at minus 5. You didn't need the other 37. You were good. So keep that stuff in mind when you're troubleshooting, and that'll help you identify some of the problems. Some other tips and kind of interesting things that you can do. You can run panel mode on an imported mesh. So the same rules apply that for the panel guidance. So that being said, like a CAD STL is going to be very unlikely a good way to go for an aero solution. The clustering is usually in completely the wrong spot, but you can bring it in if you want to. And there's another talk later in the week that kind of gets into how this can be useful. And you can also run CFD mesh grids in panel mode as long as the mesh that you give it is a quality grid. If you have, say, a single section wing or even a multi-section wing and you're trying to apply dihedral at the root section, put a small constant 0 dihedral section down at the root, particularly because even in VLM mode, this gap is going to cause a problem. So if you put a little constant 0 dihedral section here, it's going to make that nice and watertight, and your problems will typically go away. In the viewer itself, you can use the minus or plus keys to look at how everything's, the different agglomeration meshes that go into the solution. So if you see those and they are somehow anti-symmetric, something has gone wrong and you should check your grids again. And for running in, say, VSP Aero in the command window, if you are trying to figure out the way to execute that well, if you run the GUI, the very first line in the console output is the command line that you can just copy and paste, and it will do exactly the same thing from the command window. So a good way to set up something a bit more advanced to run in the command window is to run something from the GUI to automatically set up most of the input files, tweak all the input files to have the interesting stuff in it that you want, and then run it from the command line. And if you have some of these distributed propulsion arrangements where you have lots of propellers and you get tired of setting thrust and power coefficient and RPM all the time, use links. Just link all of the propellers together if they're all supposed to have the same values, or you can use advanced links. And that's a really fast way of setting everything at once. So use that stuff to your advantage. And of course, for unique problems, bug reports, issues, use the OpenVSP Google group, because either Rob or Dave or myself or anybody else that's involved in the community, lots of really experienced users, will jump in and we'll try and help. You know, we might not get back to you in an hour or two, but we'll usually have about 24-hour turnaround time, and we'll do our best to help you along. So that's what I've got for VSP Aero modeling. I know I've tried to kind of clip through, and we're about 5 minutes behind on some of the VSP Aero demos. But really, the demonstrations here are going to be kind of an informal process where I'm showing you how you can make things work well, some things that are going to make VSP Aero break, and you know, we'll show you a bit of the things that you can do to help yourself along. So appreciate that, and I'll go ahead and get VSP pulled up. And Rob, if there are any questions that I need to answer in the meantime, just let me know.
Not at this moment. We had maybe one pulled up that I answered through text, but I think you're doing all right.
All right, great. Let's see. I'm gonna give us some room here. Set it up like my ground school videos and give us some room. All right, so let's see if there's some stuff that I can bring up here. Demos. All right. So I'll bring this up, and seems like everything's still working okay. Let me pull up my notebook here so that I know the types of things that I want to get to while I'm doing this. All right. So, okay. In this demonstration, we're going to talk a little bit about where the that blunt trailing edge airfoil can come from and how you can avoid it, and we'll do a bit of a live demonstration on how to alleviate some of this. So what I've done here is I've loaded in an airfoil from Xfoil that's basically a NACA 2412, and this airfoil automatically comes out with about a 0.2% trailing edge gap, and you can see that here if you go to the Modify tab. The closure automatically calculates what this is. So it's relative 0.00252, but in reality, it's about 1/100th of a foot in the length units that I'm using right now. So it's definitely there. And kind of like we talked about in the presentation, we can change this from flat, and we can either go to round, which, you know, lofts it around like that. But if you want something nice and sharp, you can go to edge. You can go to sharp. You can see there's a slight difference in how exactly these little tessellated bits are being applied, but edge is usually pretty good. And then you can do things like adjusting the closure. So if you don't want to play with the length, where you can adjust how this is, or even set it up or down using offset, let's say we go back to flat, we can then adjust the closure here, and instead of 0.1 in absolute thickness, we just drag it back to 0. And you can see that it adjusts the upper and lower surface and collapses that down to a single point. That is now a sharp edge all the way along back to this point. So those are a few ways that you can adjust these, say, blunt trailing edges that are brought in from an airfoil file, is a very common cause of this, and sharpen it back up so that it works in panel mode. Let's see. So in the meantime, we can take a look at one of the others that I wanted to show you. And this is a bit of a dual demonstration. So we've got we've got a basic wing here. I've given it about 21 sections, and under the plan tab, we're going to make sure that our leading edge and trailing edge clustering is good. And then we're going to give this some clustering out at the tip. So let's set that to 0.25. And very quickly, we're going to run VSP arrow in VLM mode for just 1 point, just to get the point across. We don't necessarily have to set anything else up. We're going to use the shown set and run it. So it's going to run real quick, no problem. And what we'll notice here is the loading looks good, but you'll see that there's this gap right here in the middle. Now that's perfectly normal, because in VLM mode in particular, you'll see that each of these loads are being calculated in the middle of the strip. And so it's treating these as the one on the right side and the one on the left. So it's not giving you any information at all about this in the middle. And so it's okay if you see this and that these lines aren't connected. Just know that it's plotting all of these points together in a line, because that involves the right-hand surface of the wing. The other side's the left-hand surface. So don't be bothered about that little guy. Now, if we, say, screenshot this, just to keep it in mind, and put that over here for now, we're going to do another demonstration where we do some winglets. So I'm going to show this, I'm going to no-show the other one, and we're going to bump the size of this out a little bit, and we're going to watch what happens when we have winglets on this. So in this case, we're at 0.2, so let's make this one 8.8 and make it reasonably similar to that other one. And now we have a winglet set up out here at the edge where it's got a 45-degree bend, and then it goes straight up to 90. And you'll notice that I've got rotate foil to match dihedral turned on right now. If I turn this off, what it does is it flattens this vertical section down into effectively a flat plate. So if I press R, pick a point to rotate around, that's what that looks like. And that's not going to work very well. So if I were to use the shown set, launch the solver, you can see it's already having a hard time, lots of iterations to try and get down, and you'll see stuff like this. So this is an indicator of a bad solution, because there are these giant peaks where something has gone very wrong. And that is one of the things that you can use to try and identify where these problems exist. And so if we take a look at that in the viewer, and I'll bring this over here so you can see what's going on. If I show the pressures, you can see that there's this really nasty pressure spike right over here. So it's causing all sorts of issues. If we show trailing wakes, I didn't set it to where it should extend these further out. So you can set far distance to something like 100 to really get this to roll up. But on one side, it seems relatively well behaved. On this side, it's actually like throwing them outward. So already you can tell that there's something wrong with this. So if we come back in here, rotate the foils, and take a look at this again, now you can see that the foils are all rotated to be effectively normal to the surface here, and it's following the dihedral, bends around, and then this has some thickness. So you'll notice out here in the corner that OpenVSP is trying to make sure that these are all normal, and it's kind of blending it in as you move along. That's okay. I know it's not the absolute full thickness of this airfoil that's supposed to be there, but it captures pretty much all of it. So if we go ahead and launch again, we should get something that looks quite a bit better. Now this is more like it. You see that we don't have any of these weird negative peaks down at the bottom. You know, we have a section of the wing where there are a whole lot of points being computed effectively out at the edge of the span, but we knew that. But you can see that the distribution is relatively similar. So if we come in and take this snapshot, and then we're going to bring it over here, paste it in, and do a side-by-side of these two solutions, then you can see, well, if I would have been smart and put my scales where they were supposed to be, effectively what's happening is the winglets are moving this span loading out farther. So you can see that really it doesn't drop off until about 1. So here at the edges, this little drop off where you lose something out here is getting pushed out. So it is capturing the effects of the winglet. And if we were to come in to launch the viewer and take a look at this as well, you'll see that the pressures are all nice and even, and that the trailing wakes are all well behaved. So looking at that, there aren't any weird pressure spikes, and in fact, if we come in and take a look at the contour legend, this is all, you know, order of magnitude expected behaviors, especially here in this primary region. We're only going from about 0 to ballpark of -2. So everything is looking good there. Let me back out of this a little bit and clear up my workspace so we can talk a bit more about this. Let's see here. So I suppose while I'm at it, I could show you an example of, say, a vertical forward face or a blunt trailing edge failing in panel mode. Let's see if I can bring that up. Common model release. Let's take a look at that. That's a different one. So apologies for the delay there, folks. I'm trying to find the one that works well enough for us. This might take a while. And part of the reason this model takes so long to load into OpenVSP is because there are a whole lot of propeller components in here, and it has to build every single one of them. So there we go. Now we're in business. So while we're at it, let's go out and take a look at this tip nacelle, and we'll point out some of these areas that that will cause problems in the solver. So specifically, if we start here and show only, you'll see that there are vertical faces both here on, say, the inlet to the motor surface. There are blunt faces down here on the back of the spinner. There are blunt faces in between the motor. And even in the simple version where you have all of this, say, combined down to a single nacelle, these vertical faces exist. And so you want to try and avoid that by doing something like coming back to this section and picking a cross section. Here we go. Going out to the last cross section. So the closure's a point. You see that the delta X is like 0 here because this is all built out of a stack. If we stretch that out just a little bit, something like, let's give it 1/2 inch. That might even be too much. So something like 0.1 or 0.05 is going to be plenty. Something like that is going to run in panel mode. It's going to run in VLM mode. It's not going to give you any issues. So those are a few things that you can do to identify some issues with your solution. You can look for errors in your model. Those are some ways that you can avoid things that will cause problems in your vortex lattice or your panel solutions. And really, it's where you should start when you're trying to troubleshoot some of these more complex models. And again, build things from the ground up. Build your complexity as you go. Don't start with something like the X57 detailed model and do something wild like expect to just turn on all of the propellers and get something meaningful out of the solver. Because chances are that's not going to work. There's too much going on. And in fact, this model, the detailed version, is more intended for building up either an outer mold line for component layup or for higher order CFD, where all of these different components can spin. So if you're just looking for something to run through VSP Aero, by all means, pick the simple one, and even then you have to kind of refine it a little bit. Let's see here. So it's about 2:20. I tried to shave a little bit of that time back so we had time for a little break before M4 Engineering jumps on. and starts to give us some updates to their work over the last year or so. Rob, are there any other questions that have popped up, or does anybody want to see a particular demonstration? I think
There was one or two questions that I think I've already answered. I'd say, I think it's always neat to just do a very simple, maybe a rotating blade case, just to show folks who've maybe never looked at that, how quick and easy it is to set up
oh, sure.
and analyze a rotor.
Yeah, we can do that, and I think that's a great idea because that'll help us point out maybe some of the outputs that come and what we can use for that as well. So let's maybe set this to 2, set this to 1. Just for fun of it, let's say Mach 2. I know someone asked about a supersonic case. Not really sure what's going to happen here, but let's run it anyway. Yep. So, I mean, it ran. Whether that is that's particularly meaningful with such a poorly resolved model, you know, but it will work. VLM mode runs supersonic cases, so go for that. So, all right, let's do a propeller case, and in this one, let's just do an isolated propeller so it runs a little bit faster. We're going to add a default propeller, and let's take this down to something like, say, a 2-foot diameter, and we'll run. Actually, you know what? There's a better way to do this. Let's open our examples here. We're going to do isolated rotor, and we'll open this one. So this is an example that comes with OpenVSP that Dave Kinney has set up for the purposes of demonstrating this mode. And so you can see it's a 5-bladed prop. It's got a diameter of 10. It's, relatively simple. And we'll go ahead and jump into VSP Aero. And so under the Advanced tab, you'll see you turn on rotating blades. We'll give this a few more CPUs to make it run quicker. And you'll notice that there is both a free stream velocity, a reference velocity, and a Mach reference. And as has been asked in the Google group numerous times, what's the difference? Well, for slow free stream cases and even zero free stream cases, you need, either for actuator discs or in the case of rotating blades, you'll want a reference velocity so that the solver has something to normalize everything. So in this case, by turning on the VREF, you're telling it that the reference velocity that it should use for calculations is this value, and then it applies the free stream using a second value. Because this is all potential code, you can think of the reference velocity and the Mach number and even the Reynolds number as kind of disconnected from one another. So it's up to you to make sure that that all of these are scaled appropriately. We'll go ahead and give it some wake nodes and maybe give it some far field distance to make sure that we capture enough of the wake. And then here under the propeller tab is where you start playing around with some of the settings. So you'll notice that Dave talked about this 860 RPM. There's that. If you have multiple versions of this, you can tell it a uniform RPM and it will apply it to every single one of these rotors. And you can either have auto time stepping, or you can set the time steps accordingly. So for this, let's just set it to auto time step, back it off to say 6 revolutions so we don't spend all day doing this, and make sure that all this stuff makes sense. Yep, looks good. And so from here, we're just going to launch the solver. And so what should happen is it's going to set everything up, and you can see that because there aren't a whole lot of points, it's a linear twist, linear taper, it's a relatively simple propeller model. You can see that each one of these steps is only taking about 3 iterations to get down to convergence, which shows you that everything is behaving relatively well. And so even for the case where we're running 6 revolutions in an unsteady time stepping, this is going at a pretty decent clip. Now again, I'm throwing 8 processors at it and not using hyperthreading, but you get the idea. It may take a little bit longer on your machine, but it's a very stable run. So while this is running, just keep in mind that, again, you want to use some best practices for your vortex lattice set up. You want to make sure that your clustering is good on your blades, that you get more information out of the tips where, your tip vortices are going to be. That's going to help the solver converge faster. That's going to help the run go faster. So while this is plugging along, Rob, have I missed anything in the chat or anything else going on?
In particular, someone asked if all these videos were going to be made, broken apart, and made available as individual segments in the future.
Yes, absolutely. So just like we did last year, we are recording the live session, and I will cut all of these videos up into individual talks. So as long we'll have the slides from each of the presenters included on the 2021 workshop page, and the video link to each individual talk will be right next to it. So it'll be just like the 2020 workshop. Yes.
And that was the only question right now. There was a request to do a quadcopter in hover, and maybe if we still have time, I'm not sure that we will, but maybe if we still have time, you could do a minimal case of a quadcopter in hover, just for fun. But this will probably suffice.
Yeah, I'll say, for a quadcopter in hover, especially rotating blades in unsteady mode, VSP Aero, at least from what I've seen, is going to do it, and it's going to do it pretty darn well. Especially if you do something like the hover ramp where you let it kind of ease down into hover and then stabilize. Dave would be able to speak much more accurately to the quality of that solution. I have relatively limited experience trying to run it in that configuration, mostly because it takes quite a long time, and I haven't had a design that I've been particularly trying to find. But if we have some time, we might be able to run an example case where we use, say, 4 rotors and piece them together and just put them around a body. I know M4 is supposed to start here in about 4 minutes, which should be just enough time for us to take a look at this solution and take a look at some of the results and then move on. But I will let everybody online know that M4 is scheduled to run to about 3:15. It's about a 45-minute talk. And if we have some time at the end of the day, which we should have about half an hour, maybe 45 minutes, where we can come back and revisit some of these topics and kind of play around with OpenVSP a bit and do some, quick, easy demos like that. So we should have time to come back and do some more demos here after this next talk. So if we don't get to it, then we'll see. So we're just coming up on the last time step here. All right. And so what you're going to see here in the load distribution when the results manager comes up is the load distribution of your thrust coefficient. And in this, I think H is what, Rob? Is that helicopter?
Yeah, that's just a denotation. The helicopter community uses a different set of coefficients than propeller community. And so the _H means that it's using the helicopter conventions, whereas when we don't have that underscore, it means it's propeller conventions.
All right. Yeah, so you'll see that, we have all 5 of the blade surfaces. All of the loading is exactly the same. There's not really reason it wouldn't be. And then you can look at the actual load itself. So if we're talking about the lift coefficient per blade. But most of you're probably going to be interested in the unsteady solution. So you see it's kind of noisy here at the beginning, and then it loads up and kind of evens out. So if we're looking at things like the thrust coefficient, it gets nice and even and steady. But you'll see that you have different data type selections here, where you have the rotor, the group, and the history file. So the history, you'll see what we want here, CFX. There's nothing here, there were no bodies that contribute to the history file. And so there are also no groups. All of these are rotor components. So if we get into a bit more of, say, the dynamic groups input file, that's how VSP Aero knows which one of these is which. So we can take a look at things like the torque coefficient, and you can see that it, gets nice and stable. Very quickly before we jump on and let M4 take over for their talk, we'll take a look at the solution in the viewer. And we'll throw some pressures on there and some trailing wakes. And notice that we have 121 of these solutions. So every single time step is included, and you can step through these. And as the wake advances, you can even hold this button down and it'll kind of animate a little bit. But the longer it builds up, the more information it has to keep track of. So you'll notice it starts to bog down a little. Just fast forward all the way to the end if you want to, and you can see the fully developed wake here in the background, and it shows you how all this is behaving. Now, if you run this and you start to see this wind up into a nasty tumbleweed, or you see it doing some things to where it starts to bounce all over the place, chances are your time stepping is wrong, or you have an improper resolution here on your blade. So beware of that. All right, so Thomas and Tyler from M4, are you guys on the line? You want to do an audio check real quick?
Yes, hello. Can you hear me?
I can hear you.
Hello, this is Thomas. Can you hear me?
Yep, it sounds great. So I'm going to bring you guys over here, and you are welcome to go ahead and start your presentation.
Okay, let me see. So I need to share my slides, right? Because I couldn't see those when you were doing that.
Yes.
Okay.
Yeah, it has to do with how the stream is set up. I have to pick one or the other. If I'm presenting, I've got to run mine from my computer.
Got it. Okay, cool. Can you guys see my slides?
We can see it, and I'm gonna go to focus mode and try and get rid of all of this extra stuff around the edges. And you are welcome to go.
All right, great. Well, thanks everybody for attending our session. So we're gonna present some of our recent updates, and also we'll have a live demonstration at the end. So yeah, let's jump right into it. Okay, I guess the overview. So I didn't really want to spend a lot of time on going through the Structure Studio overview and some of the stuff that we've shown in the previous workshop. So I'll probably blaze through that pretty quickly and focus on the third bullet there, which is our recent developments and some future work. And then after we're through that, I'll hand it over to Thomas Nishinzi, and he will discuss an X57 Maxwell demonstration and hopefully be able to do that live for everyone so they can see that. Okay, so just a refresher for folks, and again, I'm going to go through these quickly. M4 Structure Studio is a software that we've developed in-house, primarily for predicting structural weight for unconventional vehicles, and we've integrated this tool with VSP. So this allows you to bring in VSP geometry and rapidly set up detailed structural analysis models for structural weight prediction. Kind of showing a quick review of our flowchart here. We kind of have six blocks that we proceed through. Our first step is a sketch point layout process where we'll add hard points to the OpenVSP components that we want to create structural models for, structural representations of. Once we do that, we'll move on to our sketch block, which allows you to specify really all the kind of details that are needed to build up that structural analysis model. So we're going to define kind of the connectivity of our sketch points that create ribs and spars in your wings, for example, or bulkheads and floors in your fuselage, as well as loads, boundary conditions, optimization, material properties, all the things that are kind of needed to tie together an optimization ready structural analysis deck. Once you've done that, you'll run our M4 Structure Studio FIM and merge capabilities, which will generate component FIMs for each of the components that you want to model structure for. It'll tie those together based on the way that you specify you want to bring those components together, and build kind of what we call a complete merged vehicle, which is shown there in the bottom center. And at this point, you're basically ready to run Nastran. So you put that model into Nastran and you'll run, for example, a design optimization for Solution 200 type study subject to load cases and stress restraint constraints, and generate your sized vehicle. And then once you're done with that, you'll bring that back to our weight tool where you can generate a comprehensive weight statement. And this is a very detailed weight statement that allows you to slice and dice the weight by components and custom groups if desired. Okay, so that was very fast. Also, I'm going to throw up here quickly some of the selected applications that we've applied Structure Studio to. So here you can see, again, on the left side, all the VSP models for all these various different configurations, ranging from rotorcraft, commercial transports, electric GAs, hail vehicles, eVTOLs, BWBs, etc. here, and then their corresponding Structure Studio model that we've simulated and analyzed. Okay, so now I'm going to get into the new stuff. So recent developments and future work. So some of the big things that we did this time. So last time we showed that we had support for Mac and Windows. We've now added support for Ubuntu version 20.04 LTS. And another thing that we worked on here is this crash load analysis capability. And really the goal of this capability was to develop kind of a simplified or basically represent crash loads and criteria that are kind of appropriate for conceptual design. And so we've drawn upon the MIL standard 1290A load cases, as well as FAR Part 27, and created kind of this conceptual approximation where we're looking really for like a fast running kind of simpler model that's representative of the detailed analysis. You know, traditional crash simulation, you might have an LS Dyna model, for example, where you're interested in looking at nonlinear structural, fluid, soil, solid interactions and various failure mechanisms. Those detailed models typically take long run times for them to be simulated and obtain those accurate kind of physical representation of the crash simulation. So we wanted to do something that was more representative of conceptual design. So what we've done is more or less created this total force calculation that's done on peak acceleration and max gross takeoff weight based on crash loads that you've chosen, where we have point forces on selected locations of the vehicle. Here, right, you can see we've shown just like one of the NASA UAM quad rotor vehicles there. With a crash loads there on the rear landing gear, shown in some results from that simulation. Moving on, another addition that we've added is our rotorcraft software integration. So we've developed kind of an integrated capability with XGen, Intelligent Cross-Sectional Generation tool, which is really a tool that's kind of a preprocessor for VABs, which VABs is a variational asymptotic beam section analysis tool. It's essentially a tool that's used to create composite rotorcraft blades. And we've essentially allowed now connection with that, which I'll talk about a little bit more in the next slide, with Infrastructure Studio models. And then ultimately along with RCAS for doing rotorcraft comprehensive analysis. The other thing here we kind of listed as at a very high level mini usability improvements. There's awfully too many to list here really for this presentation, but I've called out a couple of the kind of the handy ones that have been implemented in the last year. Shown on our right here, we have this sketch card copy and paste. So now we can actually copy cards and paste them. So if you ever get in the mode where you feel like you're creating too many cards and it becomes kind of tedious, the copy and paste functionality really expedites that process, as well as this card deletion, undo and redo capability, kind of handy features for expediting through the tool usage there. We've also added material normal and orientation visualization capabilities, and that is super helpful when you've got composite material systems that you're trying to make sure your material coordinate systems are correctly aligned in the direction that you're expecting them to be when the structural model gets built. So we've kind of added a capability for that, and you can easily correct any normals or misaligned things that you detect in your model. Okay, moving on to our XGen RCAS tool. So really kind of the essence of this capability is that we have these Infrastructure Studio analysis models that we can generate, kind of shown here in the top left, where we've more or less modeled structurally the primary components except for the rotorcraft blade. So then you could combine this with, say, an XGen blade model, which we can kind of show down there in the bottom left image. And taking these two structural analysis models, combine these together using our utility here that we've integrated into the Structure Studio software. into a templatized input deck for RCAS. And really this is using a kind of a modal response representation of the Structure Studio model that gets input into RCAS along with a templatized file for the XGen Blade details. And all of that will feed into RCAS, and you can run a simulation within RCAS and basically extract those loads. So if you wanted to get rotorcraft loads out of RCAS, you could do that, and then bring those loads back into Structure Studio and resize your fuselage representation. I guess a key thing to point out here is that we are not trying to reinvent GRCAS or any kind of tool like that. We're essentially basically creating an integrated capability to bring in these data into RCAS. The user still has to define all of their own load cases kind of on their own on the RCAS side of things. We don't provide any kind of utilities for that. Okay, so with that, we're kind of moving on to the end here, the future work. So bunch of future developments, potential future developments on our radar. We've looked at potentially integrating with additional geometry tools. We've had some interest for basically developing additional on-ramps to the Structure Studio process, as well as replacing the Nastran kind of structural analysis capability with other tools. Get a lot of folks that are interested in using kind of open source analysis structural tools there. So that's something that we're looking at. As well as basically developing additional post-processing capabilities. Once you've analyzed your model and you've done the weight statement generator, it's useful kind of to look at some specific details regarding your model in addition to just the weight, and some of those capabilities might be nice to have in the tool as well as certain customer feature requests that we've received. One thing I did want to call out is we are a part of this NASA University Leadership Initiative, or ULI, round 4 that came out, I believe it was last summer. And our proposal, our team, which is a larger effort of I believe 9 other team co-Is. This is led by UCSD and John Huang. This rapid development of urban air mobility vehicle concepts through full configuration, multidisciplinary design analysis and optimization effort will be kicking off, I believe next week. And this is a 3-year effort, which will leverage some of the developments shown here. All right, I'd just like to acknowledge NASA SBIR program, NASA Ames, Langley, and Army Ames, as well as the CCRPP program for funding these developments. All right, so now I'm going to hand it over to Thomas to discuss the X57 Maxwell demonstration.
Okay, thank you. Let me just share my screen. All right, can you see my screen? All right, so I'm just gonna, how do I fix this? All right, there we go. So I'm gonna be doing a kind of a live walkthrough of how to create a model in Structure Studio, and I just wanted to go through basically before I do that live, an overview of what I'll be doing. So the first step is to import an OpenVSP vehicle into M4 Structure Studio. Then I'm going to lay out sketch points on the OpenVSP model, or on the OML, and then once that's done, again, initialize the sketch model, and that's kind of the main model in M4 Structure Studio, where the user will have to define all the components via cards. So those cards are, material and property cards, structural cards, arrow cards, optimization cards, and then once you've defined all your components, you then specify how all those components will be merged together, and you do that with merge cards. And then you can make all the analyses you want by defining load cards. And then in this example, I'm just going to be doing a normal modes analysis as just as a simple analysis. So I'm going to actually take the X57 Maxwell simplified model off of the VSP hanger, and I'm going to actually import it directly into M4 Structure Studio. And M4 Structure Studio actually has the OpenVSP API under the hood. So what we're looking at there is like the actual like surface querying of the model. So then you lay out sketch points on the OpenVSP model. And then in this example, I'm only going to be looking at 4 components: the wing, the fuselage, and then the vertical and horizontal tail. You could model all those nacelles, but just for simplification, I'm going to be ignoring those. But I will be adding some non-structural masses for the big outboard motors as for demonstration. When you're doing this, you only lay out sketch points on half the component. So as you can see, the fuselage, it's only being the points are only on the port side, and then on the wing, it's only on the top side. And that's kind of that's because it's. I'll get to why that is in a bit on the next slide. But and then additionally, for symmetric components, you only have to define it for half. So for only one of those symmetric components. So that wing, I only have to define it for the starboard wing there. So then the next step is to convert that into the sketch model, which is a 2D representation of every component. And as you can see, it's kind of apparent why you only need to define the sketch points on half, as it's a 2D model. And then each component has its own sketch plane, so that fuselage is a vertical plane, while that wing is a horizontal plane, and that lets you define through structures such as ribs and spars on the wing, or bulkheads and floors on the fuselage, very simply. So the first step is you get all those points from the sketch point layout, and then you define and then you can see here I've defined the through structure. So the red lines correspond to bulkheads on the fuselage, while the red lines correspond to ribs and spars on the wing. And then here you can see I've added these blue elements for our skins, and that basically means there's going to be structural elements on the OML at those locations. And then I've also added some non-structural masses, which I like these orange lines connected to a point, and those represent the rotors in this example. So then after you've done all that, you basically just click a button and it generates a mesh and all the analyses, and then you can use the tool of your choice to view those results. All right, so now I'm going to switch over to the live demonstration. So the first thing I'm going to do is download the Maxwell. So I'm going to search for it. You got to download the simplified version. And then I'm going to put it foldered by itself, so it's nice and contained. Then I already have M4 Structure Studio open, and this is kind of the what the GUI looks like with nothing loaded.
Thomas, we're only seeing your PowerPoint screen.
Oh, I think my what screen was being presented changed. Let me fix that. Is this better? All right, good. All right, so yeah, I downloaded the X57 Maxwell from the OpenVSP hanger. I created a folder and just put it in it, and then I've launched M4 Structure Studio. So to import the model, you can just drag the VSP3 file into M4 Structure Studio. It takes a little bit to load it, but as you can see, we have the OpenVSP model here in M4 Structure Studio, all the components on the left. And you can change how it's visualized too. So you can view it as a surface, or with the hotkeys, wireframe. I stick with the wireframe. So the first thing I'm going to do is lay out the sketch points for the fuselage. So I'm going to right-click on the component in the tree. And I'm going to use the automated fuselage layout tool. So you first have to choose what the sketch plane is. I'm going to be choosing the XZ sketch plane, and that will, of course, so that'll let me define bulkheads and floors on that XZ plane. So I'll choose the XZ plane. And then you can choose a number of options. The main one I'm going to focus on are where the bulkheads are placed, and you can choose what parametric value you want the bulkhead to be placed at. You can change these up and down. I'm just going to click through some of these where I want to place the bulkheads. And then I hit confirm. As you can see, all these sketch points have been laid out on the fuselage. One thing I'm going to do to so that automated fuselage layout tool is just a starting point. You can go in and change where these sketch points are. So one thing that this models in M4 Structure Studio tend to like is not to come to a point like this. So I'm going to shift this grid of points aft slightly, so so they don't come to a point. So I'm going to go to this grid component on the left, and I'm going to change the four corners of it. So I'm going to change the U1 value to 0.1, and then the U4 value to 0.1. So that shifted the whole grid back ever so slightly. So now we have, instead of coming to a point, it's these 5 points here. And then I'm going to do the same thing for the aft. I'm going to change 2 to 0.925. 3 to 0.925, and then I'm going to just, so you can see it better, same thing at the back, not coming to a point. All right, so next I'm going to, so that's all the sketch points you need for the fuselage. And those sketch points, again, will be used to define structural components and various other things for the fuselage. I'm going to look at the wing now. For the wing, I'm going to use the XY sketch planes. So looking down on it, that'll let me define ribs and spars on the XY plane. So if I go to the clean wing, I'm going to use the automated wing layout tool. So XY plane, and pretty simple GUI right here. I'm going to choose 9 ribs and just 2 spars. And then I'm going to shift these are the parametric coordinates for the leading and trailing spar. So I'm going to just move those inward a bit. So confirm. As you can see, we now have all these sketch points placed on the wing. So one thing, I mentioned I wasn't going to model these nacelles, but something that the user is probably going to want to do is have all these sketch points on the wing line up with these nacelles. So I'm going to do that real quick. So I can go in and change the various columns of sketch points here, and I can move the one end of it up and down. So I'm just going to move this one down a bit so it lines up. That one looks fine. These sketch points, move them up a bit. These up. Same with these. Not being too precise here. And then it looks like I kind of have one too many here, so I'm just going to delete this line of points. Just delete that, and then move this one down, and then these two points out here are fine. All right. So now that the wing's done, I'm not going to do any more work on that in the sketch point layout tool. So now I'm going to look at the horizontal tail and the vertical tail. For the horizontal tail, it's much like the wing. I'm going to use the wing layout tool, same XY plane. And I'm going to use 3 ribs, 2 spars, trailing edge of 2.5, trailing edge of 2.5. And for this horizontal stabilizer, I don't really want to model this weird little structural area back here, so I'm going to shift this grid like I did for the fuselage. So let's move it up so it's only really capturing the wing part of the lifting surface. And then I'm going to quickly space out these points by right-clicking on the columns tab and using the linear spacing tool. And this lets me define how many columns I want. So I'm going to use 4, and then I'm going to space it with their XYZ value. So you can either space it so they're all evenly spaced in the XYZ coordinate system, or you can space them evenly in the OpenVSP UW coordinate system. So XYZ, so now I have these 4 columns evenly spaced. That's good for the horizontal stabilizer. Now for the vertical tail, I'm going to use the automated wing layout tool again. And I'm going to use the XZ plane. I'm going to do 5 ribs, 2 spars, much like the other components. And then, again, I don't really want to model this little area down here, so I'm going to shift the grid up. Right, there we go. And then I'm going to space out these points differently too. So I'm going to use that linear spacing tool again, 7 columns, and I'm going to have them spaced with the UW, and those tend to match the kind of discrete airfoil sections better. All right, there we go. And then if I show all, to extents, there is the complete sketch point layout for the X57 Maxwell. So the next step is to actually create the sketch model. So we're going to go up and do initialize sketch model. So first you actually have to save the sketch point layout. So I'm just going to call it Maxwell, save it. And then you can see the 4 components that we defined sketch point layouts for appear here as tabs. And there's kind of, you also have some options on how you want, what like cards you want automatically created when you do the, once the model's initialized. So you can automatically have it add skin elements or beam elements. So these beam to columns means that bulkheads will automatically be created. And then for like the wing, the adding beams to rows and columns mean that both ribs and spars will automatically be created. You can also change the material properties of these things. So we'll just go into that for the fuselage. So you can choose a different material property for the skins or the beams. The beams are just any through structure, while the skins are the OML structure. I don't know, we'll just change this to composite aircraft skin. And then you can also make custom composites or custom shell elements. You can also choose your unit system. So that's done. Then I'm going to go to the wing. For the wing, so this column here is the prop layout. So this is how many property regions are created for the component. So this skin for every column means that a different property region will be created for every column of skin 4 elements. So that's useful for optimization where you want to change the property regions of just a small part of the wing. So you want the inboard sections to be thicker than the outboard sections. So I'm going to kind of show how you might set that up, but I'm not actually going to be doing optimization. So I'm going to do a custom P-shell. So, and then I can go in here and edit the values. I could change the material, but I'm going to just stick with aluminum. And then you can change the, so there's the thickness here. So this is the starting thickness of the property region. But I'm going to also set a lower bounds, 0.01 inches, and upper bound of 2 inches. So that means these property regions during optimization can go all the way down to 0.01 inch thickness or be increased to 2 inches. So I'm just going to do done. I'm not going to really touch the vertical tail and horizontal stabilizer. The default settings for those are fine. Hit create. And it takes a little while. It projects all these points to the 2D plane of the component. And it will also automatically create all these cards that you see now. So then, as I was saying, like in that previous section, that material cards were automatically created for every component, and then different property regions created. So as I showed you, I chose composites for the fuselage. So you can see all these different property regions for the fuselage. And then for the wing, you can see these property regions, which have those lower and upper bounds for optimization. So each of these sections could have a different thickness value, different gauge when being sized. So there's just kind of the automatically created cards. Generally, you're going to have to go in and change some of this, as automation never does exactly what you want. So the first component I'm going to focus on is the fuselage. So I'm going to just show only in Snap 2. This just basically shows only this component and snaps the camera to view its sketch plane. One consequence of flattening this the nose and tail out is that the structure is not closed here. So I'm going to add some beam elements there to close off the nose. So I'm going to go to structural elements under fuselage, beams. I'm going to open the beam wizard. This basically helps you facilitate creating beam cards using just by clicking in the model. So I'm going to choose what property region I want these new beam cards to have. Doesn't really matter. And then I'm going to use the paver multiple. So this lets you create multiple beam cards at once. So you choose the starting point and the ending point, and you click. And as you can see, it created this red line between all 5 of these points. All right, I'm going to do the same thing on the aft. Paver multiple, click on the bottom point, click on the top point, click, beam cards created. Another thing I want to do is all these red lines essentially represent bulkheads, but I don't want this many bulkheads, so I'm going to delete a few of them. Done with that. So I'm going to delete these 2,000 and 3,000 bulkheads. Delete. Delete the 5,000 to 7,000 bulkheads. Delete these, and I'm just hitting the delete key on my keyboard, and you can double check what cards you're deleting here. If any of these cards have dependencies, so if you're deleting a property and there's cards that depend on that property, it'll list them here as well, so you can see exactly what the effects of deleting is. But these cards don't have any dependencies. And then I'm going to delete the 9,000 and 10,000 beams. Delete those. And then finally, I'm going to delete these 13,000 beams. All right, there we go. I don't know if that's how many bulkheads the Maxwell actually has, but it's good enough. Next, I'm going to work on the wing. So I'm going to show this in Snap 2. As you can see, the ribs and spars have already been created. But one thing I am going to add is add some concentrated masses for the outboard motors. So go out here, I'm going to do structural elements, attachments, add attachment. And then I can go here, click on the card and the newly created card in the model and change its values. So I'm going to change its CG to 160, 287. So now we have this point out here, but it's just connected to some random point out at the center. We don't want that, so we're going to connect it to these 4 points at the end of the wing here. So I'm going to change these point IDs. I'm going to deselect point 1. I'm going to select point 41, 42, 43, 44. There we go. Now we have a, and then I'm going to add some mass to it, say 100 pounds. So now we have a 100-pound mass connected to the end of the wing here. I'm going to do the same thing for the other side. So I'm just going to copy and paste this attachment. So just created another one over top of it. I'm going to change the Y value to -200. So now it's over here. And then I'm going to change the points to the symmetric points. So instead of 41 through 44, it's 20,041 to 20,044. There we go. So I could be creating, so these nacelles could have been modeled explicitly with their own components, but I'm just using concentrated masses to model them. And then additionally, every single nacelle probably should have had its own concentrated mass and rotor, but I'm not going to worry about that right now due to time constraints. So I'm just gonna leave it to just those two concentrated masses. All right, and then show all. I don't really want to change anything in the horizontal or vertical tail, but as you can see, there's structure already created for them. The next step is to determine how all these components are merged together. So, and then the first step within that is to determine the order in which the components are merged. So if you go up to the merge steps and do the merge wizard, it lets you choose two components. So, and these are the first two components that are going to be merged together. So I'm going to merge the fuselage to the wing. So as you can see, the fuselage and wing. You hit next, and then you have this fuselage wing component. So then that's going to be merged to the horizontal stabilizer next, and then those three components are going to be merged to the vertical tail next. And then you hit finish. So as you can see, 3 new merge steps were created. So just to reiterate, the first merge is between the fuselage and the wing, and then those two components are merged with the horizontal stabilizer, and then those 3 components are merged with the vertical tail. The order isn't that important for merging this vehicle, except you probably don't want to start by merging the horizontal tail to the wing, for example, as they don't touch. And then, so the next step is to determine how all these things are merged together. So we're going to be using a stiff spring method rigid card to merge them to get all these components together. But in order to do that, you need to create attachments where they're going to be merged together. So I'm going to start with the fuselage and wing attachments. For the fuselage, I'm going to add an attachment. And it's going to be at 160, 0, 90. So it puts the point about there. And then I want to have it connect to points 59, 60, 61, 62. So that's the 4 points here. And then I want 76, 77, 78, 79. Oh, I need to remove that first point. All right, so then we have this connection here for the fuselage where it's connected to these 8 sketch points. And that basically means it'll be connected to the elements created in the FEM at those sketch points. And then I'm going to do the same thing for the wing. So I'm going to create a new attachment for the wing. And I'm going to put this at the same location as the fuselage attachment. So 160, 0, 90. So it's on top of it. And then I'm going to connect it to the wing points 1, 2, 3, and 4. Okay. All right, so now we have that wing attachment, and then we have the fuselage attachment. Now we're going to add a rigid connection between them. So under merge fuselage clean wing, we can add a stiff spring method, add rigid. And then we want to attach fuselage attachment 3 to clean wing attachment 4, as that was the newest one we created. All right, so now the fuselage and the wing are connected. One other thing that I am going to do is at this fuselage attachment, I'm just going to add 1,000 pounds to represent more non-structural masses that reside in the fuselage, like batteries. Again, probably not in the correct location, but it's close enough for this model, or for this example. And now I need to do that same attachment connections for the fuselage and the two tails components. So for the fuselage, I'm going to add another attachment. 2, 0, 7.5. That's attachment about there. And then the points, I'm going to choose 16 and 17. And then 84 and 85. So to those 4 corners. And then I'm not going to add a mask to this one. So then next I need to do it for the horizontal stabilizer. Attachment add. I'm going to do it at the same location. Did it do that right? And then I'm going to attach this to both sides of the horizontal stabilizer here. So points 1, 2, 3, 4, and then 1, 2, 3, 4 again. So now it's connected to both sides of the horizontal stabilizer. Now I'm going to do the same thing for the vertical tail. Attachment add. And then I'm going to connect this to points 1, 2, 3, and 4. So that's just the bottom of the vertical tail. All right, and then I'm going to connect all these attachments together. So I'm going to connect the fuselage attachment 5 to horizontal stabilizer attachment 6. And then here again, fuselage attachment 5 to vertical tail attachment 7. And then you can change the spring value if you want, but I'm going to just keep that at the default. All right, so right now all the structural models for this demonstration, the structural model is done. There's a lot of things I didn't include in this demonstration simply because of time reasons. But like, for example, for the wing, you can add aerodynamic elements such as aero or control surfaces. You can add frames, landing gears, fuel tanks, and many other things, or more detailed structure. But all right, so then we're merged. All right, and then the last thing I want to do is, by default, a normal modes analysis is created, and you can choose how many modes you want to be analyzed. I'll increase this to 25. And then one other thing I'm going to do is add a parameter to the analysis, param weight mass, and I'm basically just telling the analysis tool what unit system I'm using, so inches per second, or inches second, yeah. All right, so that's all done. One other thing I'm going to do is, just so this runs faster, I'm going to change all the meshing parameters. So right now the meshing size is 2, so that means the element sizes will be 2 inches. I'm going to increase this to 20, so a very coarse mesh. And then I'm going to do this for every component. Mesh size 20. Mesh size 20. Vertical tail, modeling properties, mesh size 20. So now every component has a mesh size of 20, so it'll be very coarse, but it'll run very quickly. So now the model is complete, and then we just have to hit this button, and then the FEM will be created with all the through structure and analyses. So just going to create a folder, PDFs, open it up, select folder. As you can see in the log, I don't know why I didn't make it full screen earlier. It's currently meshing the fuselage. Now it's meshing the wing. It's going through every skin element and beam element. now it's working on the horizontal stabilizer. That's the vertical tail. And then once all those components are meshed, it works on merging them together and then cleaning up any poor elements of poor quality. This should go pretty quick. And then it's done. And for us, FEM complete. And we can actually do a preliminary look at the FEM within the tool. I'm going to change this to surface view. So as I mentioned, the mesh is very coarse. You can obviously make the mesh finer if you'd like. And then we can actually compare this to the OML previously from the that we've been using from OpenVSP. But right now, I'm going to then, so this just created the FEM and the analysis. The next step is to actually run the analysis. So I'm going to use this run Nastran button. And then just select this case 103, which was that normal modes analysis. Run Nastran. Nastran job complete. Hopefully that ran okay. No fatal messages, so it looks like it ran. So then I'm going to be pulling up PyNastran GUI, which is an open source tool for viewing Nastran BDFs and results. Also developed as a side project by someone here at M4 Engineering. So I'm going to go to Maxwell BDFs and load this case. Here's our model. And then I'm going to change the transparency of this so you can see some of the through structure. So you can see these bulkheads created in the fuselage, and then you can see these ribs and spars created in the wings. And then the other thing I wanted to show was the optimization design variable regions. So if you remember, I had set lower and upper bounds for the wing property regions, and you can see all those different property regions here. But also, like I said, no optimization for sizing was actually performed, so these design variable regions weren't used, but it just kind of a demonstration of how easy it is to create all these design variable regions for sizing your structure. So then next, I'm just going to load the results. And so these are the normal modes. First few, there's the first wing bending mode. And then we can actually just animate this for fun, create animation. Let's see how the normal modes for this vehicle looks. All right. And then one final thing I wanted to do was show off the weight statement generator in M4 Structure Studio. So if we go back to M4, and we click the weight statement, generate weight statement, we can select this case 103, generate weight statement. And it'll show you all like a structural and non-structural breakdown of all the weights in this model. So again, this model wasn't sized, so none of the structural values really mean anything. But you can see the 1,000 pounds we added to the fuselage plus the 200 pounds for the outboard motors that I added. You can also see the center of gravity, the CG location. Then you can also see the different regions. So you can see that like all the skins of the wing weighed 403 pounds, or all the ribs and spars weighed 17 and 41 pounds respectively. And then you can actually look at every property region as well by itself. And then if you had run optimization, there's a column here for running for the optimized values as well. All right, and so that's kind of the end of my demonstration. Just to kind of reiterate, this wasn't so much how to make the best model in M4 Structure Studio. It's just to really demonstrate how quick and easy it is to make a full FEM model of a vehicle created in OpenVSP.
Thanks, Thomas.
And then I think one thing I wanted to leave you with is we're going to do, I guess, questions if anyone has them live, but if you want to email us any questions, you can email either myself or Tyler at these emails, or if you want to inquire about actually purchasing M4 structures through your XGen, you can email Dan at Beer.
Thomas, thanks a lot for that.
Yeah.
Really impressive to see the progress you guys have made year to year. And I think this is extremely cool to see what's possible using the API and writing an application with VSP under the hood. So really cool to see that. Definitely a power user of the API, and frankly one who never asks questions, and you must just, it's either easy or you figure things out on your own. So kudos to you.
Thank you.
There's one question on the IO list for you.
Okay.
Someone just said, this looks great for uniform structures, but what about cutouts that cross longerons and bulkheads that are cut into? So anything for that?
So we do have a capability for making partial depth structures, and it's not the, I'll be honest, it's not the greatest capability, but it's there, like you can make it work. But that is definitely something we want to focus more on in the future.
Okay.
Yeah.
Tyler, you wanted to add anything to that?
I would just add that, well, we also have that damage capability. So as part of one of the tasks for the Army, they wanted a damaged capability where you could damage the structural properties, and you can actually kind of use that in a way such that you basically set it to 100% damage. It'll intersect the mesh with a primitive object like a cylinder, for example, that you specify, and that could create holes. So it's kind of maybe a slightly awkward but way to do it with the current capabilities that are in the tool now.
Awesome. Really appreciate the demonstration, and you know, for everybody watching and following along, you know, keep in mind that a structural model was just put together for an airplane in about 30 minutes and run through. So so that it kind of demonstrates how useful and how quick it is to run through this. Granted, with an experienced hand, but relatively intuitively. So thank you guys for spending the time to update us on that, and for joining us for the workshop again this year. We appreciate it.
Yeah. Thanks for having us.
Yep, pleasure.
All right, well, that is the end of the scheduled content for the first day here of the workshop. There had been some requests for a few simple demonstrations back with, say, VSP Aero. I think we've got the time to put together a relatively simple quad rotor type setup, just for fun, just to watch what happens with 4 rotors spinning in an unsteady case. It'll be coarse, but we can do it. So if there are any additional questions, feel free to post that into the live chat, and we'll see about answering those. Or if there are any other types of demonstrations that you'd like to see today, by all means, let us know. But for right now, let me pop out of focus mode so I can get a hold of this thing. And I'll move this to the side, and we can start playing around with a simple quad rotor demo, as long as everything pulls up correctly. Widen this out just a little bit. Okay. So again, first thing I'm going to do is pop in just regular old propeller geometry, maybe scooch this over so we can see everything that's going on. And I'm going to rotate this in Y. Now here's a fun little demonstration. Notice how it takes a little while to update propellers because you're actually changing things. Even with faster update, there are things that are moving So what we can do is we can change from blades to disc. And now if I come back here and start toying around with this, it's effectively real time because it's not trying to loft the blade every time I move it. So we've got this disc mode set up, and we'll give it, let's say, some Y location, and make these each say 5 foot. Why not? Set that up to 10. Give it some XZ symmetry. And while we're at it, let's see if we can do YZ symmetry and move this in X. There we go. So we have 4 rotors from one component. Not too bad. Let's make this -5. There we go. So just for fun, that's all put up. If we go back and go to blade mode again, you'll see that we have our rotors. In the interest of time, we can come to the General tab and take a look at some of our tessellation. We've got U and W at 12 and 17 right now. That's not too bad. We probably don't need to run 12 sections for this demo, so we can do something more like, say, 9. And then in the More tab is where you have access to all of your clustering. So in this case, our leading edge and trailing edge is already set up for VLM mode. We can leave the root down at 1. Let's say bump that to 0.25 for our tip clustering. And we could give it a little bit more in W, but for the sake of time, let's just let it run. So notice here that we have all of these propellers set up around this central axis where this is effectively where the component is attached to, and we've moved it over here. But we've got the thrust vector. So the blades are all turning in this direction, and the thrust is pointing up. So we can tell that as these things rotate around in their normal direction, they're going to be trying to lift this fake body off the ground. So we can do something like drop a pod in here, and we can bring it forward a little bit, maybe bring the fineness ratio down, make it a little chunky, maybe 5, why not? So this is a really big quad rotor, but let's just see what happens here in a minute. And, you know, for no reason whatsoever, let's pop in a simple wing just to have a little fun. So we can...
Brandon, when you apply symmetry, it will cause the opposite rotor to rotate the opposite direction when you do planar symmetry. And so these will actually rotate the way they should for a quad. If instead you use radial symmetry, say you wanted to do a hex, because the way radial symmetry works, they would all rotate the same way. So you would be better off doing 2 sets of 3 or a set of 3 and applying radial symmetry for 3 and planar symmetry to get the reflection to 6.
Yeah, that's a really good point to make. So while Rob is talking about there, you'll notice that each of these, because of the way that OpenVSP interprets the way that they need to turn, you'll see that this one is going to be turning the correct direction. This one's turning back the other way. So they are all symmetric to one another. If, however, we turn this off and turn on, say, Z symmetry, they are all turning right hand. And so as we increase the number here, I hope I didn't just crash VSP because I tried to, yep, there we go. Overkill. Let's try and type in 6 and make sure I don't hurt myself. So all of these are turning in the same direction, and that's not exactly what you want. So let's go back to none and turn our symmetry back on here, and we'll jump into VSP Aero and start playing around with some of these settings. So we'll run VLM and let it go ahead and move fast. We only need to do one of these, maybe just a small alpha. Give it some forward velocity and use that to normalize everything. So under the Advanced tab, I'm going to give it all of the physical processors that I've got, and we'll do 64 wake nodes and some far field distance of, say, 100 to give the wake some time to kind of bend and do things. And we'll turn rotating blades on. So for V infinity, if we're talking about a Mach number of 0.01. Let's set this to something like, say, 30. And then for VREF, because we're going to spin these a little bit faster, we can set it to something like, say, 450 and 0.4. These numbers aren't going to be exactly right because I'm just kind of eyeballing it. And then here, our RPM, you can see uniform RPM is turned on. Let's just back that to, say, 860. It's kind of a similar value to what was done in the demonstration earlier, and you'll see that all of the RPMs have updated. Now, we don't necessarily need to go to 5 revolutions this time. We can back it off to, say, 4. And let's show what happens when we start from steady state. And so, yeah, it's only 3:30. So we have some time to let this thing kind of chew through. And we'll show what happens. So let's go ahead, and I almost broke my own rule. Save often. I'm going to jump up and save this as a VSP Aero demo. Save this as quad. Because if VSP crashes, I won't be able to get any of that back. So now we can always start where we left off. And okay, so let's launch the solver and see how it goes. All right, so it's chewing through. You can see that it's taking a little bit of time, and it's going through the time step 1 5 times so that it does the steady state. So it's initializing everything before it starts stepping through in time. You can see that now our time steps are advancing, and everything is converging and reducing the order of magnitude in about the same amount of time. So hopefully nothing is too wild in the solution right now. If we start seeing these grow and grow and grow, it means that the wakes tangled themselves up, and we probably didn't get a good solution, but that's okay too. Let's see here. I see there's a no. Everybody's been answering here in the conferences IO, which is good. So it doesn't look like anything is currently unanswered. We're doing all right. And so, again, this is, an unsteady case. These are moving bodies. I remember there was a question in the live chat about going over some of the dynamic case setups. And as soon as this is done running, we can kind of open that up and take a look and dive a little bit into the text files for a dynamic run. I don't necessarily want to bore everybody to tears while I'm doing that anyway, so I don't think it will hurt anything for me to go and dig into that while we're doing this. Let's see here. That's there. So while that's kind of running in the background, we'll take a look at these files. Let me move this out of the way so I can make sure everything's still working well. So here's what we're looking at as part of the dynamic files. So we've got the VSP Aero file is the input to the run itself. The groups file is what designates everything as either a fixed or a dynamic component or a rotor. And then you've got the group file, you've got the rotor file, so there's rotor 1, rotor 2, and then, there's a group 2 file. So in each of these, if we pull them up and look at them, we've got, come on, here we go. So this is what the VSP Aero input file looks like for this, which is pretty much the same as you would see for any other run, except for when you get down here and it starts talking about time steps. So when you say time step is -1, that's telling it use auto time stepping. And then when you have -4, it's saying use 4 rotations of the unsteady rotor. you can set those to be positive values, say time step of 0.005 or 1 times 10 to the minus fourth, you know, whatever you need, and then give it a certain number of time steps, and that works as well. And then down here at the bottom, you can see that the number of unsteady groups is 5. 4 of those are propellers. So the fixed part is the pod and the wing, and then the unsteady propellers are the 4 individual bodies on the outside. So if we take a look at the groups file, not to be confused with a group file, groups with an S, this is where it defines what each one of these components are. So you'll see that in the fixed group, we've got 3 components. This includes both the left and right side of the wing and the pod. So we identify those components here, and it says that the geometry is fixed. You can specify, you know, the orientation, but because it's fixed, all of this can be 0. That's not a problem. And then below you have each of the propeller components. So it identifies how many, what it belongs to, is it a rotor, and then it gets things like the diameter, the origin, so where it's located in space, what rotation vector is attached to that, and the omega, or the radial velocity. And so each of these are automatically generated from the GUI, but if you need to go in and change them manually, you're welcome to. And so here we see that our run's complete. So, you know, we're back to load distribution, but if we look at blades, we can pick one. And again, here's a, you know, the load distribution on that blade. And here are the unsteady results. So for the thrust, it's got all 4 of the rotors. Each of them are up here kind of hanging around 80, 90 pounds. But what you should notice here, especially with the time history, is that because I didn't really do my homework and make sure that all of these were posed very well, over time we start to get noise in this. So you can see how these are starting to shake and cause a little bit of disruption out here. If we ran this even further, we'd probably see these start to grow. And what you see going on there is that, one, the mesh or the grid is kind of poorly refined, which we already knew, and 2, that the time stepping and the RPM and the size and everything that I gave it is probably a bit unrealistic. So let's go ahead and take a look at the viewer and see how this solution looks. So I'll maximize this and zoom in a bit, and let's show our pressures and our trailing wakes, and we'll go ahead and use our contour legend. So right now there is no information, we haven't stepped through anything, so it's all 0. And then in the first step, that is the result of our steady state start. So everything runs as if it's a regular VLM mode. It attaches wakes to everything and initializes. So now our contour is set up accordingly. And then as we start to step through, you can see, again, as Rob mentioned, these are turning the way that's intended. This one is turning this way, and because we've got symmetry turned on, the RPM is the same for every one of these, but they are turning the correct direction in space, which is pretty awesome. And so as we step through, you can see that that initialized wake starts deflecting, it starts deforming. This wake out here at the wingtip is getting sucked into this propeller back here, same story back here. And all of this stuff is kind of interacting with each other. And so we're kind of clipping through, and you know, we only ran this for 4. So, you know, keep that in mind as we're blasting through these solutions. And we only had an angle of attack of 4 degrees, but we're only going really about 30 feet per second, at least according to our input. We're not going very fast. So the wakes, you can see, are kind of pushing down, but they're starting to flip and interact. These are starting to impinge on the ones back here. And we've given it enough time to where everything in the model is starting to interact, which is where some of that noise is coming from. But in the interest of, say, how long time has advanced in the model itself, you know, we only gave it, say, 100 in the far distance. You can see that the wing wakes are kind of fading out into nothing right about here. If this were going quite a bit faster, if we gave it a far distance of maybe like 500, we would probably see these wing wakes a bit farther out. But what we did, we started everything out as if it was moving and fine with that initial steady state solution. And when we turned on time stepping, we only let it advance a very small amount of time, because now we're on a rotor time scale. And some people will occasionally ask, you know, can we do things like control surface response for unsteady rotor analysis, or can we do a transition run, things like that. Like, yes, technically, but you're talking about two completely different time scales. You're talking about, you know, 10,000ths of a second or even smaller, depending on the size of your rotor and your RPM, versus, you know, a few seconds to even 30 seconds of trying to tilt a wing. So the time scales are just hugely different, and that in part is where that quasi unsteady stuff that Dave was talking about can be really, really handy. So so keep that stuff in mind as well. Let's see. So I'm trying to remember, was there anything else that I was going to demonstrate here quickly, Rob, or was that the one that we meant to go back and hit?
I think that's great. There was some question earlier today about arbitrary motion.
Right.
But I think that's probably pretty complex to set up right now. Maybe you should you know, work on something offline and have it canned so you can do a quick demo later in the workshop.
Yeah, that one, there are a couple of things that we can demonstrate for, you know, say, fully dynamic solutions, which get kind of interesting, but ones that are typically applicable for, say, tool validation cases would be like periodic motion. That is reasonably, reasonably easy to set up. And so if we don't get to it with some extra time, maybe tomorrow, we can tack that on say, Thursday afternoon. But all right, well, it seems like we have all the questions in the conferences IO page answered for today, and it looks like we at least responded to everything that we could here in the live chat on the stream today. So I want to thank everyone for joining in for the first day of the workshop here. I appreciate you all coming in and staying with us for a while. Appreciate Dave Kinney and M4 Engineering for giving their presentations and updates on these exceptionally useful tools that are integrated with OpenVSP. I want to thank Rob in particular for offering so much of his time to make this a successful event, and for backing me up. So thank you very much. And it seems like everything is for the most part wrapped up for today. So Rob, if you have any closing remarks or anything that you care to mention, feel free. Otherwise, we'll go ahead and end the stream for today, and we'll prepare for tomorrow.
I don't have anything. I'll see you all tomorrow. There should be lots more. Check out the agenda. Join us tomorrow.
All right. Well, thank you again, everybody. And remember to follow the links. Join us on the Conferences IO page to post questions and read into some of the answers. You know, you can post things in the live chat here, and we'll do our best to respond. And again, these videos are going to be, you know, sliced up and set up as individual little things that you can watch, so you don't have to search through 3 or 4 hours worth of video to try and find the one topic that you want. So we'll see you all again tomorrow. Thank you again for attending, and everybody have a good evening or day, depending on the region of the world that you're in right now. Take care.